Somewhere off the west coast of Scotland, in the cold Atlantic spray, there's a scattering of islands so small that most maps don't bother with their names. The Gavalaks. 4 uninhabited stones in the sea, worn smooth by weather, visited mostly by seabirds and the occasional geologist with a stubborn idea. If you stand on one of these islands and look down at the rock beneath your boots, you're looking at something almost impossible. You're looking at 720 million years of silence, layered like pages in a book that was never meant to be read. And yet, it was read. In 2026, a team from the University of Southampton finished counting the layers. 2,640 of them, each one a single year of sediment settling through still water, each layer thin as a fingernail. Together, they spanned 26 centuries of an ancient world. What the researchers found inside those layers is what brings us here tonight. Because those layers weren't quiet, they had a rhythm, a pulse, repeating every 4 years or so, a pattern that looked almost exactly like the El Niño cycle that shapes weather across the modern Pacific. A 9-year solar cycle still recognizable. Longer rhythms too, stretching across 150 years, the kind of signals you'd expect to find in a living, breathing climate system. Except this climate system was buried under a kilometer of ice. The entire planet was. We're going to spend the next 2 hours inside that frozen world, and we're going to try to understand something that seems, on first hearing, like a contradiction. The Earth froze solid from pole to pole, ice reaching down to the equator itself. It stayed that way for 56 million years the first time it happened, and 4 million years the second. And all the while, somehow, the planet was still alive underneath. Something kept moving. Something kept ticking. And when the ice finally broke, what crawled out of the meltwater wasn't the end of a story. It was the beginning of animals. The geological period where this happened has a name that almost describes itself, the Cryogenian, from the Greek for cold and birth. Roughly 720 to 635 million years ago, during an era called the Neoproterozoic, which is the last long breath of time before complex life finally took hold. At the start of the Cryogenian, the Earth looked nothing like the one we know. There was only one large continent, a drifting supercontinent called Rodinia, and most of it sat across the equator in the warm latitudes. The sun was fainter then, about 6% weaker than today. There were no trees, no animals you could see without a microscope, no forests, no fish, only microbes in the oceans and a thin film of algae. A quiet planet, mostly blue and brown, spinning slowly toward a catastrophe it had no way of anticipating. What pushed this planet over the edge was a feedback loop. And the loop itself is the single most important thing to understand about Snowball Earth, so I want to set it down gently before we go any further. Ice is reflective. When sunlight hits fresh ice or snow, about 92% of that light bounces back into space. Dark ocean water, on the other hand, absorbs almost everything. This difference matters because a planet's temperature depends on how much sunlight it keeps versus how much it throws away. So if the Earth cools for any reason, even slightly, some new ice forms at the poles. That ice reflects more sunlight. The planet cools a little more. More ice forms, and on and on. Most of the time, this loop is stable. The cold air at the poles has less moisture, so ice growth runs into natural limits. A balance holds. But physicists and climate modelers figured out, back in the 1960s, that this stability has an edge to it. If ice ever spreads far enough toward the equator, something like 25 or 30 degrees of latitude from the equator itself, the feedback stops being a gentle slope and becomes a cliff. Past that point, ice advances on its own, unstoppable until the entire surface is frozen. No volcano, no ocean current, no shift in the sun can reverse it. The planet locks. This was a theoretical prediction for decades. No one thought it had actually happened. The climate models even had a problem with it, because once the Earth froze, the models couldn't figure out how it would ever thaw. A planet that reflective, that cold, should stay cold forever. The math said so. And then, in the 1980s and 1990s, the rocks started telling a different story. Glacial deposits showed up in places that had been sitting at the tropics 700 million years ago. Tropical sediments stacked directly above ancient glacier debris, with no buffer in between. Warm, then cold, then warm again. Geologists in Namibia and Australia and the Canadian Arctic kept finding the same pattern over and over on every continent they checked. The evidence pointed to something the models said was impossible, which meant the models were missing something. That's really what this story is about. It's about a planet that froze in a way the physics said shouldn't happen, came back from that freeze in a way the physics had to be rewritten to explain, and in the gap between the two, handed us the first complex life on Earth. The ice didn't just survive, it did something to the biosphere that nothing else in the last 3 billion years had managed to do. It sorted us into existence. Before we go any deeper, a small request. If this is the kind of story you want to fall asleep to tonight, and you'd like more of it in the coming weeks, the subscribe button helps more than I can explain. Leave a comment too if you feel like it. Tell me where you're listening from and what time it is for you. It means something to know which corner of the world the voice is traveling to. And then, if you're ready, let's go back. 700 million years. Equator. 1 kilometer of ice under your feet. Let's stand there for a while. The place you're standing is what we would one day call equatorial Africa, though the continents won't arrange themselves into that shape for another 600 million years. Right now, 700 million years before anything resembling today's world, this patch of rock is part of Rodinia, and Rodinia sits mostly in the tropics. The sun climbs steeply overhead each morning, barely tilting away from vertical. In any sane version of Earth, this would be a belt of rainforest and warm ocean, shallow seas teeming with algae, air so humid it feels like drinking. But that's not what you find here. What you find instead is white. A flat, endless, almost blinding white that stretches to every horizon. The tropical sun is doing its work. It just isn't doing much. The reason the sun isn't warming anything is that most of its light is being thrown back at the sky. Snow and fresh ice reflect around 92% of what hits them. You've probably noticed this on a bright winter day, the way the glare off a snowfield can hurt your eyes in a way sand or water never quite does. Here, that effect is global. The planet is wearing a mirror, and the thin atmosphere above it is dry in a way you've never experienced, because without open water, the air can't hold much vapor. No clouds form most days. The sky is a hard, clean blue, the kind of blue you see at high altitude, a blue that feels close enough to touch. Under your boots, the ice goes down roughly a kilometer, 1,000 meters. The exact number depends on where you are, and glaciologists still argue about the finer points, but the rough figure is solid. At the equator, something like a kilometer. Nearer the poles, possibly more, 1.5 kilometers in places. To picture that, imagine 3 Empire State Buildings stacked underneath you, all of them made of ice, none of them moving. That's what separates your boots from the water below. And there is water below. This is one of the strangest facts about Snowball Earth, and it took a while for anyone to believe it. Underneath that kilometer of ice, the ocean never froze solid. It couldn't. The Earth's own internal heat, leaking up from the deep interior, keeps the water at the base of the ice just above freezing. Geothermal heat and the thermal conductivity of ice work against each other, and the balance point sits at roughly the temperature where liquid water survives under pressure, maybe 1 or 2 degrees below zero, with the salinity working in its favor. So there is an ocean down there. It's dark because no sunlight reaches it through a kilometre of ice. It's low in oxygen because the atmosphere can't exchange gases with a sealed sea. It's slow, sluggish, rich in dissolved iron that has nowhere to oxidize. A quiet, chemical ocean, waiting. The surface where you're standing is considerably colder than the sea. Models suggest the tropical surface temperature during a full snowball event hovers around -27 degrees Celsius on average and drops much lower in winter. That's roughly what the interior of Antarctica registers today during the darkest months. The difference is that Antarctica has oceans around it, moisture in the air nearby, a sense of weather. Here at the Cryogenian equator, there's almost no weather at all. The hydrologic cycle has more or less shut down. What little water moves through the atmosphere does it by sublimation, ice going straight to vapor without passing through the liquid phase and then freezing back out somewhere else as frost. Snow falls occasionally in thin dustings, but the kind of storms you know, the rain and the squalls and the heavy clouds, those belong to a wetter planet than this one. What you do have is wind. Cold, dry, insistent wind, scouring the surface of the ice. In some places, the wind has polished the ice so smooth it looks almost like glass. In others, it has built small dunes of grit, because there is dust here too, blown in from the few patches of exposed rock that still poke through. The continents aren't entirely buried. On Rodinia, some of the higher ground, the mountain ranges and the elevated plateaus, still stick up above the ice sheet as bare stone, weathered by cold. You can see them on the horizon sometimes, dark shapes against the white, and from a distance they almost look alive, like the last honest thing in the landscape. If you stood here long enough, you would notice the sun doesn't move the way it would at higher latitudes. At the equator, the path is nearly vertical, up and down, with little seasonal variation. Day and night are close to 12 hours each, as they always are here. What changes is the way the day feels. In the morning, when the sun first lifts off the horizon, the ice glitters in a kind of pink. Midday, it becomes almost painful to look at. Late afternoon, the light tips into a long, cold gold. And then night, and the stars, very many of them, in a sky that has no clouds to hide them. A half moon rising over an ice sheet lights the surface well enough to read by, if there were anything to read. Now, I want you to try to feel the time scale of what you're standing on. This wasn't a bad winter. It wasn't a 1,000-year cold snap, or even the 100,000-year rhythm of the Pleistocene ice ages we half remember through our ancestors. The ice you're standing on has been here, in roughly this form, for tens of millions of years. 40, 50, possibly more, depending on exactly where in the Cryogenian you've arrived. If you tried to count back to the last time this patch of equator saw open water and rain, you would count past every human civilization that has ever existed, past every mammal that has ever lived, past the dinosaurs, past the first fish, past the first shells, and still not arrive at the thaw. That's the kind of time we're dealing with. The psychology of that duration is worth dwelling on, because it's the thing the models struggled with more than any other detail. A short freeze is one thing. A snap event, a regional glaciation, even a global one that lasts a few 100,000 years, the math can absorb that. But tens of millions of years of stable, planet-wide ice? That requires a climate system that has genuinely forgotten how to thaw. Every day for 50 million years, the ice has held. Every sunrise has hit the mirror and bounced most of itself back into space. Every night, what little heat the surface managed to gather has radiated out into the darkness and gone. The planet isn't dying exactly. It's just stopped trying. And yet something is happening here that will eventually break this silence, though nobody on the ice, if there were anyone on the ice, would be able to see it. Underneath the kilometre of frozen water, in the dark, the slow machinery of the deep earth is still running. Volcanoes somewhere are still erupting, pushing gases up through vents in the seafloor and occasionally through the ice itself. The mantle beneath the crust is still moving, currents the size of continents turning over in ways no living thing can perceive. Plate tectonics hasn't stopped. The Earth has gone quiet on the outside, but its interior is as loud as it ever was, and that fact, which seems trivial from where you're standing, is the single thread that will eventually pull this whole frozen world apart. For now, though, there is only the ice, the mirror, the cold, steady wind, the sun that does almost nothing, and the silence that goes on and on. 56 million years of it, the first time. And if you think that sounds like a dead planet, you would be wrong. There is a place, much later in geological time, where we can still read the heartbeat of this world, year by year, pulse by pulse. It survived because somewhere, somehow, something on this planet kept moving to a rhythm. We're going to find that rhythm now, in a stretch of rock that has no business existing. The Garvaleks sit in a stretch of sea between the Isle of Mull and the mainland of Scotland, 4 small islands that most people, even in Britain, have never heard of. Aileach and Nauim, Garb Aileach, Dún Chonhuil and Achuli. Names in Scottish Gaelic that mostly describe what you'd see if you rode past them. Rocky, rough, crowned with a ruin, wind-scraped. There are no roads on the Garvaleks. There are no permanent residents. The only real visitors, most years, are sheep, seabirds, and a handful of people curious enough about a 6th century monastery to make the crossing. And lately, a small rotation of geologists who have started to understand that these islands hold something almost impossible to find anywhere else on Earth. What the geologists come for is not dramatic to look at. It's a grey-banded rock face cut vertically into the cliff, the layers stacked so neatly they almost look printed. If you ran your hand across the surface, you'd feel the texture change every few millimeters, rough to smooth, smooth to rough, the kind of pattern a patient hand might have drawn with a pencil. The formation has a name, the Port Askeig Formation, and it dates to the Sturtian glaciation, the older of the 2 Snowball Earth freezes. You are looking, when you stand in front of this cliff, at something that was laid down while the planet was almost entirely covered in ice. And every one of those thin layers is a year. That's the discovery. That's what changed the story. In a paper published in early 2026, a team led by Thomas Jernan and Chloe Griffin at the University of Southampton, working with a research fellow named Elias Rugen, who had spent 5 years on these islands in all weathers, completed a careful count of the layers in a single long section of the Port Askeig cliff. They counted 2,640 of them. 2.5 millennia, preserved layer by layer in stone, from a period of Earth history when the climate was supposed to be doing nothing at all. The technical name for a layer like this is a varv. The word comes from Swedish, and it refers to any sediment band that forms once a year in still water, usually at the base of a lake or a quiet sea next to a glacier. During the warmer months, meltwater carries coarse grit off the ice and deposits it in the water. When the melting slows in the cold season, only the finest clays keep settling out, drifting down through water that has gone almost motionless. Over 12 months, you get a coarse layer followed by a fine layer. 1 full year, preserved as a couplet, a few millimeters thick. Stack enough of them on top of each other, and you have a calendar written in mud. Varves like this are rare from the Cryogenian. Most rocks that old have been crushed, stretched, heated, or otherwise mangled by the billion years of tectonic activity since they formed. The Port Askeig Formation somehow slipped through the rough handling. Its layers are intact, its edges are crisp, and when you analyze their thickness year by year, you're not looking at noise, you're looking at information. Here is what Griffin and her team did, and here is why the result is strange enough to be worth sitting with. They measured the thickness of each of those 2,600 layers, one after the other, and then ran the sequence through a statistical technique that searches for repeating patterns. If the climate were doing nothing, the layer thicknesses would be random. If the climate had a rhythm, the thicknesses would reflect it, because thick layers mean more meltwater and more sediment carried in, which means a warmer year, and thin layers mean the opposite. What came out of the analysis was not nothing. 4 distinct cycles emerged, each of them strong and statistically clean, a cycle that repeated every 4 to 4.5 years, a 9-year cycle, a longer one at roughly 14 to 17 years, and a very long one somewhere between 130 and 150 years. If you know anything about the climate of the modern Earth, those numbers will sound familiar. The 4 to 5 year cycle matches the El Niño Southern Oscillation almost exactly. El Niño is the tropical Pacific's slow back-and-forth shift between warm and cool phases, the thing that makes California wetter some winters and Australia drier, the rhythm that fisheries and farmers and insurance companies pay attention to. It's a product of feedback between the tropical ocean and the atmosphere above it. You need an ocean for it to work. Open water, with the sun hitting it directly. The 9-year cycle lines up with a known solar variation, a rhythm in the sun's magnetic activity that still modulates weather today. The longer cycles match other known solar and oceanic patterns. None of this should be possible on Snowball Earth. The textbook version of the hypothesis, the version Joe Kirschvink proposed in 1992 and Paul Hoffman extended through the 1990s, held that the oceans were almost completely sealed. If the surface is frozen everywhere, the atmosphere can't couple to the sea. The heat flows stop. The moisture stops. The pressure cells and trade winds and monsoons that give the modern Earth its weather, all of that requires open water somewhere. A planet under ice, by this logic, should be climatically dead. Cold, yes. Stable, yes. But flat. A single long note held for 56 million years with no rhythm inside it at all. What the Gavelach rocks say is that the note was not flat. The climate modeler who worked alongside Griffin and Gjernan, Min Min Fu, ran simulations to figure out how this could have happened. She tested several versions of a Snowball Earth, one in which the entire ocean was sealed beneath continuous ice, one in which a narrow band of open water survived at the equator, and one in which the tropics held larger patches of ice-free or thin ice sea, a configuration geologists sometimes call a water belt. Only the water belt version produced the full set of rhythms the rocks had recorded. You needed open water somewhere, even if it was modest, even if it was a fraction of what the modern ocean offers. Give the atmosphere that much and the old cycles come back. Give it less and they fade. This matters for reasons that go beyond one section of rock on a Scottish island. For almost 3 decades, one of the quieter disputes in geology has been between 2 camps. The hard snowball camp argues that the ice was essentially total, pole to pole and shore to shore. The slushball or waterbelt camp argues that some open water must have survived in the tropics because photosynthetic life survived, and photosynthesis needs light, which means the ice couldn't have been everywhere. The hard snowball side has had the stronger geological signature on its side, things like the banded iron formations and the thickness of the glacial deposits. The slushball side has had biology on its side, and a kind of common sense about how life persists. What the Gavelach Varves do is give the slushball camp something it didn't have before: a rhythm, a physical record of atmospheric dynamics operating in real time, on a timescale you can hold in your hand from the middle of a snowball event. It doesn't close the argument, but it tilts it. What the rhythm also tells you, if you let yourself sit with the implication, is that the planet during a snowball is not really the way we first imagined it. It is not a white marble, uniform and dead, spinning through space and waiting for a volcano to rescue it. It is a planet with weather somewhere, with ocean motion somewhere, with a sun that still rises and sets, and with patches of water that still feel that sun and respond to it, however faintly. The frozen Earth had a heartbeat. It was quiet, and most of the planet's surface never heard it, but it was there, and it kept time for 56 million years. Imagine Griffin walking the Garvalach cliffs for the first time. Grey stone, grey sky, waves hitting the base of the rock, wind loud enough that you have to shout to be heard by the person next to you, a hammer in her hand, or more likely a small chisel, because the layers are too delicate for brute force. She works her way down one particular section of the formation, tapping, collecting samples, marking the bands with a pencil. Back in the lab, under a microscope, she looks at a thin slice of the rock and sees the couplets clearly, the pale and dark pairs she has been counting for months. Each couplet, a year, and somewhere in that long sequence, her software pings, a 4-year rhythm, a 9-year rhythm, patterns that have no business being there, looking back at her across 720 million years. There's a phrase her colleague Jernan used later when the paper came out. He said the finding was jaw-dropping, that the climate system has an innate tendency to oscillate, even under extreme conditions, if given the slightest opportunity. I think about that line a lot. The climate system has a tendency to oscillate, even when most of it is buried, even when almost everything has gone still. Give it a crack of open water, a thin seam of sunlight on a tropical sea, and the old rhythms come back. The planet remembers how to breathe. Which raises a question that takes us back to the beginning of this whole episode, the question underneath all the others. If the planet was alive down there, quietly keeping time, how did it ever get this way in the first place? How do you push a world with oceans and atmosphere and weather into a state cold enough to lock it under ice for 56 million years? The feedback loop does the final work, the runaway slide from a cold planet to a frozen one. But something has to start the slide. Something has to tip a balance that, most of the time, is stable enough to resist being tipped. The first push came from a volcano, or more precisely, from what a volcano left behind. A field of black basalt sitting in the hottest, wettest part of the ancient world, doing something to the atmosphere that nobody at the time could have seen, and that almost no one since has fully appreciated. The volcano that started this is gone now. Not in the way a volcano usually disappears, eroded slowly over tens of millions of years until nothing recognizable is left. This one is still there, in pieces, but the pieces have traveled. What was once a single enormous expanse of black rock laid down at the equator of an ancient world has been carried by plate tectonics into the Canadian Arctic. Today, fragments of it sit on the islands north of Hudson Bay, in places with names like Victoria Island and Baffin Island, in landscapes of tundra and permafrost where summers last a few weeks and winters swallow the sun. If you stood on one of those fragments today, you would be standing on a basalt that was born in heat and humidity under a tropical sky 719 million years ago. Geologists call it the Franklin Large Igneous Province. The name is deliberate. A large igneous province is not an ordinary volcano. It isn't even an ordinary volcanic field. These are rare, continent-scale eruptions, the kind that happen only a handful of times across the history of a planet. And when they happen, they change things. The Siberian traps helped end the Permian and took 96% of marine species with them. The Deccan traps were already pouring molten rock across India when the asteroid that killed the dinosaurs arrived. These events don't behave like familiar volcanoes. They flood whole regions with basalt over timescales of 1 million years or so, producing volumes of lava that are hard to picture even when the numbers are written down. And the Franklin, in its moment, was one of the largest magmatic events the geological record has ever preserved. The timing has been nailed down with extraordinary precision in the last few years. Uranium-led dating of zircon crystals from the Franklin basalts puts the main eruptive phase between 719.86 and 718.61 million years ago, a window of about 1.25 million years, give or take. The Sturtian glaciation begins, according to the best dates we have, somewhere between 900,000 and 1.6 million years after that, which means the Franklin erupted, covered an enormous patch of the equatorial world in black rock, and then the ice started, not over tens of millions of years, essentially back to back. For a long time, people suspected a connection but couldn't prove one. The conventional guess, the one that floated through geology textbooks for decades, was that big volcanic episodes like this one pumped so much sulfur into the stratosphere that they caused a volcanic winter, a cooling event severe enough to tip the planet into runaway ice. Think of a supervolcano like Pinatubo in 1991, which dropped global temperatures by about 0.5 degrees for a couple of years. Scale that up to something 1,000 times larger, sustained for much longer, and maybe you get a snowball. It was a reasonable guess, but when the dates came back, the geometry didn't work. Volcanic cooling from sulfur fades within years, not millennia. 100,000 years is not a stretch you can bridge with aerosols. Whatever the Franklin did to the climate, it did slowly, and it did through something more patient than sulfur. What the Franklin actually did, we now understand, had nothing to do with what came out of the volcano's mouth and everything to do with what it left behind on the ground. Basalt, the black volcanic rock that forms when lava cools, has a specific property that turns out to matter enormously here. It weathers. Meaning, when basalt sits in warm, wet conditions and gets rained on for long periods, it doesn't just erode physically, it dissolves chemically in a particular way. The minerals in basalt, things like olivine and pyroxene and plagioclase, react with carbon dioxide and water to form clays and dissolved ions. Calcium, magnesium, silica, bicarbonate. Those ions wash into rivers which carry them to the sea, where the calcium and bicarbonate combine to form limestone on the seafloor. At the end of that whole sequence, a molecule of carbon dioxide that started out in the atmosphere has been locked into solid rock. It has been, in the language of the carbon cycle, sequestered. This process happens everywhere on Earth, all the time. It is, in the long run, the most important thermostat the planet has. Volcanoes pump carbon dioxide into the air. Rain weathers silicate rocks and pulls it back out. The two processes balance over millions of years, and the balance determines how much greenhouse warming the atmosphere provides. When the planet gets too warm, weathering speeds up because there's more rain and higher temperatures accelerate the chemistry, and the extra drawdown cools things off. When the planet gets too cold, weathering slows, carbon accumulates in the atmosphere, and warming returns. It's a negative feedback, and it has kept Earth's temperature within a survivable range for most of its history. The reason the Franklin mattered is that it didn't just add a small amount of basalt to the global weathering budget. It added an enormous amount, and it added it in exactly the wrong place, or from the planet's thermostatic point of view, exactly the right one. The Franklin erupted almost squarely on the equator. At those latitudes, rain falls more or less every day, the air is warm enough to drive chemistry quickly, and there is nowhere for the new rock to sit quietly and do nothing. Every drop of tropical rain that hit a Franklin basalt surface pulled a little carbon dioxide out of the atmosphere and carried it, dissolved, toward the sea. And there was a lot of rock to hit. A fresh basalt plain the size of a subcontinent, cracked and glassy and chemically reactive, exposed to one of the most aggressive weathering environments on the planet. The drawdown began slowly. Nobody on the surface of Rodinia, if there had been anybody, would have noticed it for a long time. A trace-level shift in atmospheric carbon dioxide over the first few centuries, a slight dip in the global average temperature, poles a little colder than usual, polar sea ice lasting a little longer into the summer. Nothing alarming, nothing a modern weather satellite would have flagged. But the thing about the Earth's thermostat is that it works both ways, and it works through the same feedback no matter which direction you push it. A small cooling means a bit more reflective ice. A bit more reflective ice means a bit less absorbed sunlight. A bit less absorbed sunlight means a slightly colder planet. The feedback is subtle as long as the ice sheets stay far from the equator, where most of the solar energy is landing. But as the ice creeps toward the tropics, the feedback grows stronger, because each kilometer of ice advance is reflecting sunlight from a more powerful source. This is where the runaway comes in, and this is the part of the story that the climate models of the 1960s got right, and that took geology a long time to catch up with. Mikhail Budyko and William Sellers, working independently in the middle of the Cold War, showed mathematically that a planet's ice cover can be stable in two different configurations. One is the familiar one, ice caps at the poles with open oceans and continents in between. The other is a planet almost entirely covered in ice. Between them lies an instability, a boundary where small nudges in either direction can tip the system toward one state or the other. The location of that boundary depends on lots of factors, but the central one is how close the ice edge gets to the equator. When the models calculated the critical latitude, they got something like 25 to 30 degrees. That is, if ice ever spreads to within 30 degrees of the equator, the feedback becomes unstoppable, and the planet rolls the rest of the way into a total freeze within 1,000 years or so. Nobody, when those papers came out, thought this had actually happened. The math was interesting, but it seemed academic. A planet-wide freeze was the kind of thing you found in hypothetical exercises, not in the geological record. Besides, the same math had a darker implication on the other side. Once you're in the fully frozen state, the math said, you're stuck there. Ice reflects too much of the sun for the planet to warm its way out. You would need a greenhouse effect many times stronger than anything in Earth's recent history to break the feedback in reverse. The fully frozen state was what physicists call a stable attractor, and getting out of it looked impossible. It took a paleomagnetic geologist at Caltech named Joe Kirschvink to point out in 1989 and again in a short paper in 1992 that the word impossible might be doing too much work in that sentence. Kirschvink was not a climate modeler. He studied the magnetic signatures locked into ancient rocks, the kind of work that tells you what latitude a piece of stone was sitting at when it formed. And what he was seeing, in rock after rock from the Neo-Proterozoic, was that glacial deposits had formed at the equator, not near the equator, on it, within a few degrees of the old paleomagnetic equator in multiple places around the world, in rocks dated to roughly the same time. Either the Earth had tilted on its axis to a wildly unusual angle, which other evidence made unlikely, or the glaciers had actually reached the tropics. And if they had reached the tropics, the Budyko-Sellers math said they couldn't have stopped there. They had to have gone all the way. Kirschvink's move was elegant. He said, in effect, that the climate models were right about the runaway and right about the stability of the frozen state, but wrong about one crucial detail. The models assumed that nothing would change about the planet during the tens of millions of years the ice lasted. But that's not how the Earth actually works. Volcanoes don't stop erupting because the surface is frozen. Plate tectonics doesn't pause. Carbon dioxide keeps entering the atmosphere from the deep Earth, through vents on the seafloor and through sub-aerial volcanoes poking through the ice, and it has nowhere to go. The usual removal process, silicate weathering, has shut down, because the rocks are under ice and there is no rain. So the carbon dioxide builds up, slowly, for a very long time, until it reaches a concentration so high that the greenhouse effect finally overcomes the reflectivity of the ice and the planet thaws. The frozen state is not a permanent trap. It is a long pause with an exit that takes millions of years to prepare. That was the argument. A 7-paragraph chapter buried in a 1,300-page academic book, published in 1992, proposing that the Earth had been a snowball twice in its past and had escaped both times through the patient accumulation of volcanic carbon dioxide. For the first several years, almost nobody took it seriously. 2 other geologists, Cees Klein and Nick Bukes, supported the idea in print. Most of the field ignored it, or treated it as an interesting what-if. It wasn't until Paul Hoffman and his colleagues went to Namibia in the mid-1990s, looking for the specific geological signatures Kirschvink's hypothesis predicted, that the question began to move. Kirschvink had a line he used about models in a later essay reflecting on how the idea first came to him. Something to the effect that models should be used to explain observations, not to rule them out. If the rocks say a thing happened and the model says it can't, then you rewrite the model, not the rocks. It's a simple principle, the kind of thing you might hear in a first-year graduate seminar. But it required a certain nerve to apply it here, because the observation in question was that the entire Earth had frozen for tens of millions of years, and the models saying it couldn't have happened were the best models the field had. The Franklin and what it did to the atmosphere over its first 100,000 years turns out to have been the trigger Kirschvink's hypothesis needed. A trigger large enough to drag the planet's carbon balance across the critical line, positioned well enough in latitude to do its work at maximum efficiency, timed exactly enough to coincide with the start of the Sturtian ice. It was the right kind of volcano in the right place at the right moment. And after it finished erupting, it kept working, not through its vents, but through the slow chemical ruin of its own dead surface. Once the planet crossed into the runaway, though, the Franklin's role was finished. The basalt kept weathering, but it no longer mattered. A different mechanism took over, something with a far longer memory, operating on a timescale that would keep the world frozen for almost 60 million years. Paul Hoffman first went to Namibia in 1993, the year after Kirschvink's short paper appeared. He was not, at that point, trying to prove Snowball Earth. He was a sedimentary geologist with a long interest in Proterozoic carbonate rocks, the thick limestone sequences that form in warm, shallow seas, and northern Namibia has some of the best preserved Neo-Proterozoic examples anywhere on the planet. The desert exposes them cleanly, the rocks lie almost flat, the outcrops are continuous for kilometers. You can walk for a whole morning across one depositional environment and then step, quite literally, from warm water limestone onto glacial debris without a pause in between. That kind of contact is what caught his attention. Not the glaciers themselves, but the way they sat directly against the tropical rocks, with no transition, no sign of a slow cooling, no gradual climate shift in the stratigraphy. Warm, then cold, then warm again, stacked like the pages of a book that had been slammed shut and reopened. Hoffman spent, across the next 3 decades, something like 50 months of his life on those outcrops. 50 months, cumulatively, camping in the Kaokoland, walking the Otavi Mountains, mapping the Myberg and the Rasthof, and the Gob and the Kaelberg, formations whose names most geologists have never heard, but which now carry more weight in the Snowball Earth literature than any other rocks on Earth. By the late 1990s, he and his colleagues, including Galen Halvorson, who was his graduate student at the time, and Daniel Schrag, the Harvard geochemist who ran the isotope work, had built up a picture specific enough to test Kirschvink's hypothesis against. The 1998 paper they published in the journal Science laid that picture out. two separate snowball events. Tropical glaciers resting directly on tropical carbonates. Enormous blankets of peculiar limestone sitting directly on top of the glacial debris, marking the sudden return of warm conditions. The geometry Kirschvink had predicted, found in the rocks on a continent he had never visited. The older of the two events, the one Hoffman and his colleagues traced first, is what geologists now call the Sturtian glaciation. The name comes from Charles Sturt, a 19th century Australian explorer by way of the Sturt Gorge in South Australia, where some of the first examples of Cryogenian glacial deposits were described. The Sturtian ice began somewhere around 717 million years ago, within 100,000 years or so of the Franklin's final eruptions, and it lasted, according to the best dates now available from multiple continents, about 56 million years. That number is worth pausing on because it is genuinely difficult to hold in the mind. Modern human civilization, from the first cities in Mesopotamia to the present day, has lasted roughly 10,000 years. The Sturtian glaciation lasted 5,600 times that. If you ran human civilization end-to-end over and over, from the first cuneiform tablet to the latest phone in someone's pocket, and then did it again and again, you would need almost 6,000 repetitions to fill the span. The Roman Empire, from founding to fall, occupied about 1,000 years. You could stack 56,000 Roman empires back to back and still not reach the end of the Sturtian. That is the scale we are working with. An ice age that lasted longer than the entire time mammals have existed on Earth. Which raises, with some urgency, a question the models had not fully answered. Kirschvink's hypothesis said the way out of a snowball was volcanic carbon dioxide accumulating in the atmosphere until the greenhouse finally overcame the ice's reflectivity. Fair enough. But how long does that take? If the numbers don't line up, the hypothesis is in trouble. And for a while the numbers were a problem. The amount of carbon dioxide needed to melt the ice was known, at least approximately. Jim Casting at Penn State had calculated, back in 1992, that you would need about 1/10 of a bar of carbon dioxide in the atmosphere. 1/10 of a bar. That is roughly 250 times the present concentration. Several million years of volcanic outgassing, at typical rates, would do it. Several million years. Not 56. The Sturtian was not several million years of waiting for the volcanoes to catch up. It was nearly 10 times that. And, for a while, this disparity was one of the more uncomfortable facts in the hypothesis. Something was keeping the carbon dioxide from accumulating at the expected pace. Either the volcanoes were running slower than anyone thought, or some other process was pulling carbon back out as fast as it went in. Both possibilities seemed unlikely. Volcanoes are stubborn. Plate tectonics doesn't idle. And the obvious carbon sinks, weathering and photosynthesis, were supposed to be shut down under the ice. It took another 30 years of work and a set of modelling studies that only finished in 2025 to work out what was actually happening. The answer turned out to lie on the seafloor, in a process that hadn't been taken seriously in the original hypothesis because it moves so slowly that most geochemical models had ignored it. Fresh ocean crust, the basalt that forms at mid-ocean ridges and then spreads outward as the tectonic plates pull apart, reacts chemically with seawater. If the seawater is acidic, which it becomes when atmospheric carbon dioxide is high, the reaction accelerates. Carbon dioxide dissolves into the sea, reaches the young basalt on the ocean floor, and gets locked into new minerals, calcium and magnesium carbonates, growing in the cracks of the rock. It is essentially the same chemistry as continental weathering, but happening underwater on the seafloor without needing any rain or any exposed land at all. This process is always running on the modern Earth, quietly, in the background. It removes something like 5 to 10% of the carbon dioxide that volcanoes produce, a minor contributor compared to the massive continental weathering handled by rivers and soils. But during a snowball, with the continents sealed under ice and no rivers delivering weathered material anywhere, the seafloor becomes the only game in town. And it turns out the seafloor was faster than anyone expected. A team led by Trent Thomas at the University of Washington, running 10,000 model simulations with different parameters, showed in early 2026 that seafloor weathering during the Sturtian was roughly 5 times more efficient than standard estimates had assumed. Every molecule of carbon dioxide that volcanic vents released into the atmosphere had a good chance of being dragged down into the sea, reacting with young basalt and getting sealed into mineral form before it could accumulate. So the accumulation went on, but it crept. Over 1 million years, the atmosphere's carbon dioxide budget might rise by a small fraction of the amount needed to end the freeze. Over 10 million years, it might rise by a noticeable fraction. Over 30, by most of what was required. Over 50, almost all. The Sturtian was not the wait for a slow volcano. It was the wait for a leaky bucket, carbon dioxide pouring in through the vents, carbon dioxide pouring out through the seafloor, and the atmosphere filling only because the inflow was, by a thin margin, a little faster than the outflow. During those 56 million years, nothing much changed on the surface. The ice stayed where it was, plus or minus a few meters in some places, as local conditions nudged the balance. The sun kept rising and setting over a white equator. Winds kept scouring the ice. Dust kept blowing from the exposed highlands onto the frozen seas, where it settled and was buried by the next season's frost. And in a small area of what is now the Scottish west coast, which at the time was probably sitting somewhere in the mid-latitudes, year after year, sediments settled into quiet water beneath the ice. Each year, a couplet, coarse and fine, summer and winter, the rhythm the Gavelach cliffs preserved. On the continents that weren't yet called continents, in what is now Namibia and Canada and Australia and Brazil and Uruguay and Scotland, the same processes played out in parallel. Icebergs broke off the margins of floating ice shelves and drifted, or what passed for drifting on a mostly frozen sea, dropping their debris wherever the ice melted enough to let stones fall out. Those drop stones, scattered pebbles of rock sitting inside much finer sediments, are one of the clearest fingerprints of glacial deposition anywhere on Earth. Hoffman's outcrops in Namibia are full of them. Rocks the size of footballs or grapefruits or fists, sitting in soft layers of mudstone that could not possibly have carried them there by water or wind. The only thing that moves a grapefruit-sized stone into the middle of a sheet of clay is a piece of floating ice melting above it and letting the stone fall. When Hoffman walked those Namibian outcrops in the early years, he was essentially reading a ledger. The drop stones told him glaciers had been there. The carbonate rocks above and below them told him the region had been tropical before the glaciers arrived and tropical again when they left. The sandwich of warm, cold, warm, which made no sense in any of the existing climate models, made perfect sense if the whole planet had frozen and then thawed. What was missing for a long time was the precise dating. Knowing that glaciers had reached the tropics was one thing. Knowing exactly when and for exactly how long required a level of geochronological precision that didn't exist in 1998 and only gradually came together across the decades that followed through uranium lead dating refined to about 1 million years of resolution. It is that precision arriving over the last 15 years or so that finally pinned the Sturtian at 56 million years. Before the best dates were in, estimates ranged anywhere from 10 million to 100 million. The low end would have put the event in the range of a long ice age, uncomfortable but not alien. The high end would have been so extreme it was hard to believe. The truth, once it was nailed down, sat closer to the high end than almost anyone had expected. 56. A number that forces you to reconsider what kind of planet you are dealing with. For Hoffman, who is now in his late 70s and still, by last report, making occasional trips back to Namibia, the number is personal in a way most scientific findings are not. He has spent more time staring at the rocks that record it than almost anyone alive. He received the Kyoto Prize in 2024, one of the largest scientific honors outside the Nobel system, for the body of work that started in those Namibian desert mountains and, by way of Kirschvink's original 7-paragraph paper, remade an entire field. Asked once, in a quiet moment, how he felt about the whole thing, he said something to the effect that for a long time he would ask himself, many times a day, whether any of it could really be true. The evidence kept him going. That was, he said, the only thing that did, which leaves us with the thaw. At some point, after all that time, the leaky bucket did fill. Atmospheric carbon dioxide finally pushed past the threshold the models had predicted. The greenhouse caught up with the ice, and the feedback that had held the planet frozen for 56 million years began to reverse. The reversal, when it came, was not slow. It was one of the fastest climate shifts the Earth has ever experienced, and when the ice finished breaking, the world on the other side was almost unrecognizable. The first thing to understand about the end of the Sturtian is that nobody was there to see it, but if they had been, the transition from frozen to liquid would have played out fast enough to be witnessed within a single human lifetime. The feedback loop that had held the ice in place for 56 million years did not relinquish its grip gradually. It collapsed. And when it collapsed, it took the entire climate system down with it in a cascade so rapid that, from the perspective of geological time, it looks almost instantaneous in the rock record. The moment the reversal began was probably not dramatic to watch. Picture a tropical latitude, roughly where the Indian Ocean now sits, during a summer in whatever year crossed the threshold. The ice at the surface has been getting a little thinner each year, not because the atmosphere has warmed measurably, but because the slow, decade-by-decade rise in carbon dioxide has finally shifted the radiation balance just enough. On a particularly sunny day, in a particularly warm patch, a thin film of meltwater pools on top of the ice. It is not a lake. It is not even a puddle in any meaningful sense. It is a sheen, a few centimeters deep, lasting maybe a week before the cold nights refreeze it. Nothing to write home about, if anyone had been writing, but meltwater is dark. Not as dark as open ocean, but significantly darker than the snow around it. Where sunlight had been bouncing back into space with 92% efficiency, over a pool of meltwater, only about 60% gets reflected. The other 40% is absorbed, warming the water, warming the ice beneath it, making the pool last a little longer the following summer. And this, multiplied across thousands of kilometers of tropical ice surface, is how the runaway begins. Climate modelers who have simulated this process in detail, including Jun Yang and colleagues working with modern climate codes, have found that once meltwater pools start forming reliably in the subtropics, the surface albedo drops quickly enough to push the equatorial air temperature from below freezing to above freezing in something like a decade. Possibly less. The numbers are approximate, but the direction is unmistakable. Once it starts, it does not stop. Within a few centuries, open water appears at the equator for the first time in 56 million years. Within a millennium or two, the sea ice is breaking up in large areas, calving into the newly open tropical ocean. Within 10,000 years, the polar ice caps are retreating. Within 100,000, the Earth has gone from being almost entirely frozen to being almost entirely ice-free. 100,000 years is a long time in human terms. It is, in the geological record, the blink of an eye. What happened during that blink was not a gentle return to normal. The atmosphere that emerged from the snowball was carrying 1/10 of a bar of carbon dioxide, roughly 250 times the present concentration, and that atmosphere did not unwind quickly. The planet went straight from a deep freeze into one of the most extreme greenhouse states in its history. Surface temperatures in the tropics, which had been hovering around -27 °C just a few centuries earlier, may have climbed as high as 50 degrees Celsius above zero. Some reconstructions suggest even higher peaks in coastal areas where the moisture feedback was strongest. A world where equatorial seas were as warm as bathwater, where clouds piled up into storms the likes of which no modern meteorologist has ever recorded, where the atmospheric circulation was so enhanced that single storm systems could wrap around a quarter of the planet before dissipating. The meltwater pulse was violent, fast, chemically strange, and physically unlike anything the modern Earth has preserved in recent memory. And it left a signature. That is the crucial thing. The deglaciation was so abrupt and so chemically distinctive that it wrote itself into the rock record in a way that later geologists could not miss, even without knowing what they were looking at. The signature is called a cap carbonate, and it sits, almost universally, directly on top of the Cryogenian glacial deposits, wherever those deposits are preserved. A cap carbonate is exactly what the name suggests. It is a layer of carbonate rock, usually dolostone at the base, shifting to limestone above, draped across the glacial rubble like a sheet pulled over a bed. It is typically a few meters to a few tens of meters thick, which does not sound like much, but these layers extend laterally for hundreds of kilometers, sometimes thousands. In Namibia, where Hoffman's team mapped them most carefully, the cap carbonate sits on dropstone-bearing diamictite with a contact you can run a fingernail along. On one side, glacial chaos. On the other, fine-grained tropical limestone. Nothing in between. No transitional sediments. No gradual warming signal. The two rock types meet at a single bedding plane, and the message is blunt. Yesterday, glaciers. Today, warm sea. The chemistry of the cap carbonates is stranger still. Ordinary tropical limestones form slowly over thousands to millions of years as calcium carbonate precipitates out of seawater at a steady rate. Cap carbonates do not look like that. The crystal structures suggest extremely rapid precipitation. Sedimentary features include giant wave ripples with wavelengths of 10 to 15 meters, which can only form under sustained, enormous waves driven by storms much larger than anything on the modern Earth. In some sections, including outcrops in northwestern Canada and in the Mackenzie Mountains, these ripples are so well preserved that they look almost sculptural. You can walk across the top of a cap carbonate and feel the frozen motion of those ancient storms in the rock under your boots. The total amount of carbonate deposited globally across the aftermath of the Marinoan, the second snowball, has been estimated at roughly 10 to the 18th kilograms. That is a number so large it needs a reference point. Mount Everest has a mass of about 100 trillion kilograms. The cap carbonate laid down after a snowball thaw is something like 10,000 times the mass of Everest. An entire mountain range's worth of limestone precipitated out of the seawater in a few 100,000 years, blanketing the drowning continental shelves from pole to pole. Where does all that carbonate come from? It comes from the carbon dioxide in the greenhouse atmosphere mostly. The chemistry is straightforward. Carbon dioxide dissolves into warm rainwater and forms carbonic acid. Carbonic acid rains down on the newly exposed glacial debris, which is a kind of pre-crushed rock flour produced by 56 million years of grinding ice. Rock flour weathers fast because it has an enormous surface area. The weathering reactions strip calcium and magnesium out of the minerals, dump them into the rivers, and the rivers carry them to the sea. Once in the sea, the dissolved ions combine with dissolved bicarbonate, and calcium carbonate begins to precipitate. Everywhere. all at once, across every continental shelf on the planet. This is, in essence, the same process as the Franklin's weathering that started the whole mess, but running in reverse, at hundreds or thousands of times the speed, across an entire planet's worth of freshly pulverized rock. The atmosphere is bleeding carbon dioxide through every river mouth, through every storm, through every new shoreline. And the amount of alkalinity pouring into the oceans is so high that the sea goes supersaturated in carbonate minerals, meaning they precipitate spontaneously without even needing organisms to build shells. Calcium carbonate and magnesium carbonate fall out of the water column like snow, coating everything. For Hoffman, the cap carbonates were the clincher. Kirschvink had predicted something like them in 1992, reasoning that the post-Snowball greenhouse would produce exactly this kind of rapid carbonate deposition. When Hoffman's team got the isotope data back from the Namibian cap carbonates in the late 1990s, the numbers matched. The carbon isotope values were unusually light, consistent with a massive input of volcanic carbon dioxide. The pattern of precipitation was exactly what a super greenhouse collapse would produce, and the global distribution, which became clearer as other research groups found similar cap sequences on every continent where cryogenian rocks were preserved, meant the event had to be global, not a regional glaciation, not a local climate excursion, a planetary reset recorded in rock exactly where Kirschvink had said it would be. There is a physical detail here that is worth slowing down for, because it gives you a sense of just how violent the deglaciation actually was. The ice, when it melted, released an enormous amount of fresh water into the ocean, somewhere between 0.5% and 1% of the total modern ocean volume, enough to raise global sea level by tens of meters. This fresh water is less dense than salt water, so it did not mix immediately. Instead, it floated as a freshwater lid on top of the salty ocean, sometimes a kilometer thick, a layer of stratified meltwater covering most of the Earth's surface for thousands of years. Below that lid, the old salty ocean still held most of its Snowball-era chemistry. Iron-rich, oxygen-poor, preserved from the long freeze. Above the lid, in the meltwater, new water cycled violently in the tropical heat, feeding storms larger than any of the modern era, driving the giant wave ripples into the muds of the drowning shelves. When that lid eventually mixed with the ocean below, a series of chemical handoffs occurred that changed the planet's surface chemistry permanently. The iron that had been dissolved in the deep water, accumulating for tens of millions of years, finally met atmospheric oxygen when it was brought to the surface by mixing. The iron oxidized, precipitated, and fell to the sea floor as rust-colored layers, the banded iron formations that appear in cryogenian sediments on multiple continents. These layers are rare in Earth's recent history because modern oceans have virtually no dissolved iron. You only get banded iron formations when an ocean has been sealed off from atmospheric oxygen long enough to accumulate reduced iron in solution. The cryogenian banded iron formations are the fingerprint of a sea that spent tens of millions of years sealed under ice and then opened. The whole thaw, from the first meltwater pools to the deposition of the last widespread cap carbonate, probably took somewhere between a few 100,000 years and a couple of million. The uncertainty is significant because the dating is still being refined, but the direction is clear. Compared to the 56 million years of ice that preceded it, the deglaciation was fast. The transition from snowball to super greenhouse to something approaching a habitable world happened in roughly 1% of the time the ice had taken to build. And then, having demonstrated conclusively that it was possible to go from a fully frozen planet to a post-apocalyptic greenhouse and back to something like normal, the Earth did something no one entirely understands. It froze again. Between the end of the Sturtian and the beginning of the Marinoan, the planet had something like 20 million years of relative calm. Not warm by any modern standard, probably, but also not frozen. The cap carbonates that had blanketed the post-Sturtian seabed gave way, over time, to more ordinary shales and carbonates, the kind of rocks that accumulate on continental shelves during normal climatic conditions. Life, such as it was, recovered in those oceans. The microbial ecosystems that had survived the freeze and the greenhouse crisis found themselves in seas that were, for the first time in tens of millions of years, neither sealed under ice nor drowning in carbonate precipitation. For roughly 20 million years, the Earth looked almost like a world that might have been heading somewhere. Then it happened again. Around 650 million years ago, give or take a few 100,000 years, the ice began advancing from the poles for the second time. The climate slipped across the same critical threshold Kirschvink and Boudico had described. The same runaway feedback took hold, and within a few thousand years the tropics were freezing. Ice covered the continents. Ice covered the seas. Rodinia, which had continued breaking apart during the interglacial, was once again buried. And this second snowball, the one geologists now call the Marinoan, would grip the planet for something close to 4 million years before releasing it. 4 million years is, of course, still enormously long in human terms. It is longer than the entire history of our genus. If you trace the hominin lineage from the earliest Australopithecus to the present day, the Marinoan would cover that entire stretch of evolutionary time. But compared to the Sturtian's 56 million years, the Marinoan is strikingly brief, 14 times shorter. And that ratio, that enormous disparity between two ice ages that started for what looked like similar reasons and should have ended by the same mechanism, is one of the outstanding puzzles of cryogenian geology. It is the kind of puzzle that, when you start looking at it carefully, pulls you into the fine structure of how feedback systems actually work on planetary scales. The best current evidence for how long the Marinoan actually lasted comes from a set of rocks in northern Namibia that, by a kind of geological luck, preserved the event with unusual clarity. The Gorb Formation, exposed across the desert outcrops that Hoffman had spent years mapping, turns out to record the Marinoan glaciation with enough continuity and enough datable material that modern techniques can resolve its duration. A team led by Francis MacDonald at UC Santa Barbara, working with colleagues including Justin Strauss and Alan Rooney, published a paper in 2025 in the Proceedings of the National Academy of Sciences that used drone-based imaging combined with high-precision radiometric dating to pin the Marinoan at roughly 4 million years. The drones allowed them to map the stratigraphy in 3 dimensions across a scale no human geologist could cover on foot, and the radiometric dates gave them the absolute time brackets. What emerged from the combined dataset was a picture of a glaciation that began suddenly, held steady for about 4 million years, with the ice-grounding line moving less than 10 meters vertically across the whole event, and then ended. 10 meters of vertical motion over 4 million years is a striking number. It means the ice sheet was not advancing and retreating in the pulses you see in the Pleistocene ice ages, where orbital wobbles drove glaciers north and south by hundreds of kilometers every 100,000 years. The Marinoan was a hard, stable, locked configuration. The ice got to where it was going early and stayed there. For the entire 4 million year duration, the climate sat at essentially the same equilibrium point, with the planet's surface either almost fully covered in ice or, in the water belt scenario, covered with a narrow band of tropical open water that oscillated only in minor detail around a fixed position. This kind of stability is what you would expect from a hard snowball, and it strengthens the case against some competing hypotheses that had imagined the Marinoan as a series of shorter freezes stitched together. But it also sharpens the original question: If the Marinoan was just as stable as the Sturtian, and if both were driven by the same runaway feedback, then why did the Marinoan end so much faster? The answer, as far as modelers can reconstruct it, has to do with the carbon balance on the seafloor, and it connects back to the mechanism that explained the Sturtian's enormous duration in the first place. Seafloor weathering, the process that quietly pulled carbon dioxide out of the atmosphere throughout the Sturtian by locking it into young basalt on the ocean floor, depends on a few variables. How acidic the deep ocean is, which controls how fast the reactions run. How much new basalt is being produced at mid-ocean ridges, which controls how much reactive rock is available, and how much organic carbon is being buried, which indirectly affects the chemistry of the dissolved carbon pool. During the Sturtian, those variables combined in a way that made seafloor weathering unusually efficient. The leaky bucket, as I described it before, had a slow leak but an even slower fill rate, and the balance held for 56 million years. During the Marinoan, something about that balance was different. Trent Thomas and his colleagues, the same team whose 2025 modelling work helped solve the Sturtian duration problem, ran their simulations for the Marinoan configuration as well. What their 10,000 parameter runs showed was that by the time the Marinoan started, the global carbon cycle had subtly reorganised. The seafloor weathering efficiency had dropped, probably because the ocean chemistry had shifted during the 20 million year interglacial. Less of the incoming volcanic carbon dioxide was being absorbed by fresh basalt. More of it was staying in the atmosphere. So the bucket was filling faster this time. Not dramatically faster, but faster enough that 4 million years was all the Marinoan got before the carbon dioxide threshold was crossed and the thaw began. There is another possibility, a more exotic one, that has been gaining some support over the last decade: a planetary albedo perturbation, a sudden reduction in the Earth's reflectivity caused by something unusual during the glaciation that pushed the climate past the deglaciation threshold earlier than carbon dioxide alone would have done. The candidate events vary. A large volcanic eruption that dusted the ice with dark ash across millions of square kilometers, dropping the albedo enough to accelerate local melting. A giant impact that threw debris around the planet and coated ice surfaces with stones and soot. A patch of unusual atmospheric chemistry that made the ice itself slightly darker, perhaps through the accumulation of dust from nearby land. Any of these, in principle, could tip the system over sooner than pure carbon buildup would. The asteroid hypothesis is the most dramatic of these alternatives, and it was given unusual attention in 2024 when Min Fu and her colleagues at Yale published a climate modelling study in Science Advances showing that an impact comparable in size to the one that later killed the dinosaurs could, under the right conditions, either start or end a Snowball Earth. Their simulations specifically examined what would happen if a Chicxulub-scale asteroid struck an already frozen Earth. What they found was that the dust and debris thrown into the atmosphere by such an impact could darken the ice enough to raise surface temperatures by several degrees globally for decades. If the atmospheric carbon dioxide was already close to the deglaciation threshold, this kind of nudge might be enough to trigger the runaway. No direct geological evidence for such an impact during the Marinoan has been found, and Francis MacDonald, among others, has expressed open skepticism about whether any really happened. But as a model, it is internally consistent, and it points to the kind of non-carbon mechanism that could explain why the Marinoan was so much shorter than the Sturtian. Whatever the mechanism, the Marinoan ended in a deglaciation that looks, from the rock record, much like the Sturtian's. A super greenhouse, a cap carbonate sequence, giant wave ripples, a flood of alkalinity into the oceans, a precipitation of carbonate minerals at supersaturation, a planetary reset. The cap carbonate at the top of the Marinoan is, if anything, even more distinctive than the Sturtians because the chemistry of the post-Marinoan ocean was slightly different. The carbonate isotope values, the sedimentary structures, the thickness patterns, all of it is preserved on nearly every continent that holds rocks of the right age. You can trace the Marinoan deglaciation across Namibia, across the Mackenzie Mountains in Canada, across South China, across Svalbard, across Brazil and Uruguay, across Death Valley in California, across South Australia. Everywhere, the same story. Glaciers, then cap carbonate. Ice, then bath-warm tropical sea. And when the cap carbonate finished precipitating, something was different about the ocean that emerged on the other side. Different in ways that would prove to matter across the next several tens of millions of years, more than almost anything else in the Cryogenian record. The ice was gone. The super greenhouse was unwinding. The continents were still drifting, Rodinia still breaking apart, the climate still cycling back towards something that might eventually be called temperate. But the water itself had changed. What had been a nearly lifeless planetary ocean for most of Earth's history was, for the first time, beginning to behave like a place where more complex things might be possible. The details of what happened next are a story about chemistry and biology intertwined so tightly that neither one makes sense without the other. It is a story about iron and phosphorus and oxygen. It is a story about sponges and algae and the first trace fossils of creatures that could actually move. And it begins in the meltwater that was pouring off the last of the Marinoan ice sheets, carrying with it the ground-up rock of an entire frozen continent, dumping nutrients into a sea that had been starved of them for most of 1 billion years. The question of how anything survived is the one that for decades made the whole Snowball Earth hypothesis hardest to accept. You could look at the rocks and agree they said what they said. Tropical glaciers, cap carbonates, banded iron formations, the whole geological dossier. But then you had to explain how photosynthetic life came through the other side. Because it did. The microbial algae and cyanobacteria that dominated the pre-Cryogenian oceans are the same lineages that show up, essentially unchanged in their basic machinery, in the post-Cryogenian ones. Something kept them alive through 56 million years of ice the first time, through another 4 million the second time, through a combined span longer than the entire existence of placental mammals. For a long time, the simplest answer was to refuse to believe the ice had ever been global. If there had been open tropical water somewhere, even a narrow band, then photosynthetic life could have survived in it. The slush ball model, as it came to be called, was built around exactly that argument. It was physically plausible, it saved the biology, and for much of the early 2000s it seemed like a reasonable alternative to the hard snowball picture. But the geological evidence kept piling up on the other side. Tropical glacial deposits, sealed oceans that accumulated iron for tens of millions of years. The chemistry was hard to reconcile with anything other than near-total ice cover. By the late 2000s and 10s, most researchers had come around to the idea that the ice had indeed reached the equator, and the problem of how life survived had to be solved some other way. The solutions, it turned out, were more interesting than anyone had expected. The first and simplest refuge is the one nobody had to invent: hydrothermal vents. The deep-sea chimneys that spew hot, mineral-rich water from the cracks in the ocean floor were running throughout the Cryogenian exactly as they do now, and they would have supported the same kinds of chemosynthetic ecosystems they support today. Microbes that metabolize sulfur compounds, iron compounds, hydrogen, methane. None of these organisms need sunlight. None of them care whether the sea above them is frozen over for a year or for 50 million. The deep biosphere, the microbial ecosystems that live kilometers below the seafloor and derive their energy from chemical gradients in the rock, would have been essentially unaffected by the ice. They are still there today, a significant fraction of the total biomass on Earth, living in conditions that have barely changed across billions of years. The harder problem was photosynthesis. Photosynthetic organisms need light, and light does not penetrate a kilometer of ice. If the ice had been total, continuous, and uniform, every photosynthetic lineage should have died. Since they didn't, something must have been giving them access to sunlight somewhere. The question was where and how. One answer came from a surprisingly prosaic source: holes in the ice, meltwater holes specifically, that form every summer on the surface of modern glaciers and are known by a word that sounds like it belongs in science fiction: cryoconite. A cryoconite hole forms when windblown dust settles on a glacier's surface, absorbs a little more sunlight than the ice around it, and melts a small cylindrical pit down into the ice. Water collects at the bottom of the pit. In that water, if the chemistry is right, microbial life establishes itself. Algae grow. Bacteria multiply. Small communities of photosynthetic and chemosynthetic organisms live out their generations in pools a few centimeters across and maybe 20 centimeters deep. On modern Antarctic and Greenland glaciers, you can find thousands of these holes scattered across the ice surface in summer, each one a miniature ecosystem. During a snowball, with the tropical sun still beating down on the equatorial ice for a few months each year, cryoconite holes would have been everywhere the surface melted enough to form them. Not just thousands, billions. It took a long time for anyone to take this seriously as a refugium because the holes are so small, so ephemeral, so easy to overlook. But in 2025, Paul Hoffman, by then in his late 70s and still thinking about problems he had helped originate 30 years earlier, published a paper in the Proceedings of the National Academy of Sciences arguing that surface cryoconite ecosystems may have been one of the most important refugia on the frozen Earth. His argument was that the polar and alpine biomes of the pre-snowball world, the organisms already adapted to cold and ice and intermittent light, would have migrated toward the equator as the planet froze. By the time the ice reached tropical latitudes, these pre-adapted communities were ready to colonize whatever meltwater surfaces were available. The tropical ice, paradoxically, became the warmest place on the planet. It received the most solar energy, it formed the most meltwater, and it hosted the richest cryoconite communities. If this picture is correct, then during the Sturtian and the Marinoan, the equatorial ice was not a sterile white desert. It was, at least seasonally, a mosaic of dark spots, each one a pocket of life, linked loosely by windblown dust and meltwater streams. Algae, cyanobacteria, fungi, small ciliates, all of them eking out generations in the summer and retreating into dormancy in the winter. A thin biosphere, but a real one, distributed across the surface of the ice itself. Another kind of refuge existed under the ice, in the form of what researchers have started calling subglacial meltwater systems. Beneath thick ice sheets, the combination of geothermal heat from below and pressure from above can produce liquid water even when the surface temperature is deeply frozen. Modern Antarctica contains hundreds of subglacial lakes, some of them larger than Lake Ontario, kept liquid entirely by the insulating weight of the ice above. Life persists in these modern lakes, in complete darkness, sustained by chemical gradients and occasional exchanges with the surface through cracks and basal melt. The Cryogenian planet would have had equivalent systems in vast numbers, wherever continental ice sat on top of bedrock that was generating enough heat to melt its base. Every one of those subglacial lakes, if the conditions were right, could have held a microbial community cut off from the rest of the world for millions of years at a stretch. The physical evidence for subglacial meltwater on Snowball Earth was hard to find for a long time. Ice itself does not preserve. Meltwater does not preserve. What you need to find is the mark they left on the rocks below them. And in 2024, a team at the University of Colorado Boulder announced that they had found exactly that in one of the most unexpected places on the continent. The rocks in question sit in Colorado, in the area around Pikes Peak. They are granites, pink and white and ancient, part of the same basement rock that forms the spine of the Rocky Mountains today. Cutting through these granites, in narrow dikes that run for meters vertically through the older rock, are bodies of sandstone. Tavakaive sandstones, or Tava for short, named for the Ute name for Pikes Peak. The Tava sandstones have been a geological puzzle for more than a century. They are clearly younger than the granite they cut through, but their age had resisted every attempt at direct dating. They look like injected sand, as if something had forced liquid sediment into cracks in the bedrock under enormous pressure. But what pressure, and when, nobody could say for certain. Liam Courtney Davies and his colleagues, working with Rebecca Flowers at CU Boulder and Christine Sidaway at Colorado College and Francis McDonald at UC Santa Barbara, figured out how to date them. The Tava dikes are shot through with veins of iron oxide, and iron oxide contains trace amounts of uranium, which decays predictably into lead. Using laser ablation mass spectrometry, a technique that vaporizes tiny spots on the mineral and measures their isotopic composition, the team bracketed the age of the Tava injection between 690 and 660 million years ago, right in the middle of the Sturtian glaciation, when Colorado, through the accidents of plate tectonics, was sitting near the equator of Rodinia, buried under ice. What the dating means, read alongside the sedimentary structures, is that Colorado was covered by a massive continental ice sheet during the Sturtian. The ice was thick enough, over at least some of the front range of the ancient Rockies, to generate meltwater at its base through geothermal heating. That meltwater mixed with sand grains weathered off the underlying bedrock, forming a slurry, and the weight of the ice sheet above pressurized this slurry and forced it into cracks in the granite. The result was the Tava dikes, sandstone injected into bedrock by the hydraulic force of an ice sheet several kilometers thick. It is, in essence, a fossil signature of a glacial plumbing system that existed almost 700 million years ago, and the chemistry of the iron oxide veins confirms that water was actively moving through these fractures during the freeze. This is the first unambiguous physical evidence that Snowball Earth glaciation extended to the heart of continents, not just to the margins where glacial deposits are easier to preserve. It means the ice really did reach everywhere the geological reconstructions predicted. And, more importantly for the question of how life survived, it means there was liquid water somewhere on the continents during the Sturtian, under kilometers of ice, in the dark, in spaces that no photosynthetic organism could have used. But liquid water, nonetheless, connected to the rocks below, capable of hosting chemosynthetic communities that would not have cared about the absence of light. Between the cryoconite holes on the surface, the subglacial meltwater networks beneath the continental ice, the deep-sea hydrothermal vent ecosystems, and, if the Garvalach valves are read correctly, the narrow belt of tropical open water, the frozen planet was riddled with small pockets where life could persist. Not flourishing, not diversifying rapidly, just holding on. Microbial mats in the dark, algae in meltwater pools, bacteria clinging to iron-rich minerals at the base of ice sheets. An archipelago of refuges scattered across a white ocean, each one a survival capsule for a fraction of the pre-snowball biosphere. What all these refuges have in common is that they selected for something. They selected for cold tolerance, for dormancy, for the ability to wait out enormous stretches of time between episodes of activity, for metabolisms that could function on minimal resources. The organisms that came through the Cryogenian were not the same organisms that had gone in. They were the subset that could survive the kind of planet that had, for 60 million cumulative years, done almost everything it could to kill them. When the Marinoan ended, those survivors found themselves in an ocean that had been transformed. The meltwater pouring off the continents was carrying something extraordinary. Something that would, over the next 100 million years, change what it was possible for life on Earth to do. Phosphorus is one of those elements that nobody thinks about until they learn what it does. You cannot have life without it. Not any life, not any lineage, not any cell that has ever existed on this planet. Phosphorus is the backbone of DNA, the structural element of RNA, the core of the ATP molecule that every living thing uses to move energy around inside itself. Remove phosphorus from the equation and biochemistry collapses. And for most of Earth's history, phosphorus was the tightest bottleneck the biosphere had. The reason has to do with how phosphorus moves through the environment. Unlike carbon or nitrogen, phosphorus has no gas phase. It does not cycle through the atmosphere. It does not arrive on wind currents from the other side of the planet. The only way phosphorus gets from the continents into the ocean, where most of life's primary production happens, is through the physical weathering of rocks. Rain and rivers dissolve phosphorus out of certain minerals, mostly apatite, and carry it downstream. Over millions of years, a steady trickle reaches the sea, where algae and bacteria take it up as quickly as it arrives. The ocean stays hungry for phosphorus almost continuously. Primary production is throttled, oxygen production is throttled, and the whole biosphere runs at a lower ceiling than it otherwise could. This is more or less the condition the Earth was in for the billion years leading up to the Cryogenian. Low atmospheric oxygen, limited primary production, a microbial planet running on a thin budget. Some researchers have called that stretch of time the boring billion, which is unfair as a description of the science, but captures something true about the climate and the biology. Nothing much was changing. The ocean had phosphorus trickling in. It used it as fast as it arrived. The ceiling held. And then the ice sheets melted. When a continent spends 56 million years under a kilometre of glacial ice, or 4 million years, it does not emerge intact. The ice grinds. It crushes. It pulverizes rock into fragments so fine that the mineral surface area per kilogram of sediment increases by orders of magnitude compared to ordinary weathered soil. By the end of the Marinoan, the continents were covered in a blanket of this ground-up rock. Glaciologists call it rock flour, because that is what it looks like and what it behaves like, a fine, pale powder coating everything the ice had scraped over. Trillions of tons of it, across Rhodinia's fragments, across every continental shelf that had been buried. A prepared meal for the oceans. And when the ice melted, the rain did the rest. Rock flour is enormously more reactive than ordinary rock. The grains are tiny, the surfaces are raw, the minerals inside them have not yet been weathered down to their stable residues. Tropical rain, falling on fresh rock flour, dissolves the phosphorus out of it almost immediately. Rivers carry the dissolved phosphorus to the sea. And because the super-greenhouse post-Marinoan atmosphere was driving storms larger than anything in modern climate history, the rivers were running harder than modern rivers do, carrying their loads faster and in greater volumes. The result, reconstructed from the chemical signature preserved in post-Marinoan sediments, is a phosphorus pulse into the ocean that lasted perhaps a few 100,000 years, but delivered more phosphorus to the sea than the previous 100 million years had combined. Estimates of the magnitude vary, but the best recent work, from a team led by Eva Stuken, working on cap carbonate and shale sequences around the world, suggests phosphate concentrations in shelf seawater increased by something on the order of 20-fold. 20 times the normal supply. All at once. Planet-wide. What phosphorus did to the ocean was what fertilizer does to any garden, only at a scale no garden has ever seen. It fed primary production. Cyanobacteria, the photosynthetic microbes that had been running at the edge of their nutrient budget for most of 1 billion years, suddenly had more food than they knew what to do with. Their populations exploded. Mats of them formed in coastal waters. Vast blooms spread across the shelves, and every one of those cells was doing what cyanobacteria have been doing for nearly 3 billion years, which is photosynthesizing, splitting water molecules, releasing oxygen as a waste product. The ocean that had been almost entirely anoxic throughout the Cryogenian, sealed under ice with no access to atmospheric gases, now started to oxygenate from the top down. That oxygen had somewhere specific to go first, and this is where the banded iron formations come in. I mentioned them briefly at the end of the deglaciation, but they deserve a longer look because they are one of the strangest and most diagnostic rock types in the geological record. A banded iron formation, when you see one in outcrop, looks almost artificial. Alternating layers of dark iron-rich rock and pale silica-rich chert, stacked in rhythmic bands millimeters to centimeters thick, repeating for tens or hundreds of meters of vertical section. Lake Superior in North America has them. The Hamersley Range in Western Australia has them. The Transvaal of South Africa has them. Most of the iron ore that modern industry mines, the steel in every car and every building and every bridge on Earth, comes from banded iron formations laid down in the deep past. The odd thing about these formations is that they almost all date to a single narrow window in Earth history, between about 2.5 and 1.8 billion years ago, coinciding with the first rise of atmospheric oxygen. After 1.8 billion years ago, they essentially stop. The ocean becomes too oxygenated to hold dissolved iron. The iron precipitates wherever it is produced. The conditions for banded iron formation disappear. For nearly 1 billion years, there are no significant banded iron formations in the rock record. And then, in the Cryogenian, they come back. The reason they come back is that the snowball oceans had been sealed. Under the ice, with no contact with atmospheric oxygen, the deep sea had gone anoxic again. Iron leaking from mid-ocean ridges and hydrothermal vents had accumulated in the dissolved ferrous form for tens of millions of years because there was no oxygen to oxidize it. By the end of the Sturtian, the deep Cryogenian ocean held more dissolved iron than any ocean in the previous billion years, and when the ice melted and the cyanobacterial bloom began pumping oxygen into the surface waters, that oxygen met the dissolved iron at the boundary where surface and deep waters mixed. The reaction is straightforward. Oxygen plus ferrous iron plus water yields ferric iron oxide, which is rust, which is insoluble in seawater, which falls out of the water column and settles on the seafloor as a layer of red-brown mud. If the oxygen supply fluctuates from seasons or from storms or from variations in the intensity of the cyanobacterial bloom, you get alternating layers of iron-rich mud and iron-poor silica. Bands, hundreds of them, thousands of them, a rock type defined by its rhythm, each band a record of the ocean's chemistry at the moment it formed. The Cryogenian banded iron formations are thinner and less extensive than the ones from 2 billion years earlier, because the iron reservoir was smaller and the event was briefer, but they are unmistakable, and they appear on every continent where rocks of the right age are preserved, which is exactly what you would expect if the oxygenation was global. In Death Valley, in the Flinders Ranges of South Australia, in Uruguay, in Namibia, in central China. Every one of them the same story. Ice melts, phosphorus pours in, cyanobacteria bloom, oxygen accumulates, dissolved iron precipitates, rust falls to the seafloor. While all of this was happening in the ocean, something parallel was happening in the atmosphere. The oxygen that the cyanobacterial blooms were producing did not all get consumed by iron oxidation. A significant fraction of it diffused upward into the air. Atmospheric oxygen concentrations rose. not dramatically at first. The modern atmosphere is about 21% oxygen. The post-Marinoan atmosphere reached perhaps a quarter of that figure, maybe a bit more in some estimates. But it was the highest oxygen level the Earth had seen in its history, and it was climbing. This is the event geochemists call the Neoproterozoic oxygenation event. The name is long and the acronym is ugly, but the event itself was as important as anything that has ever happened to the surface of this planet. For 3 billion years, oxygen had been rare. Life had existed for most of that time, but it had existed as a microbial phenomenon, most of it anaerobic or tolerant of only trace amounts of oxygen. The few organisms that could use oxygen directly, that could run their metabolism on it rather than tolerate it, had been constrained by how little of it was available. After the Marinoan, the constraint loosened. The oxygen ceiling rose, and the organisms that had survived the snowball in their various refuges, now swimming in water that was, for the first time in 3 billion years, genuinely breathable, began to do things they had never been able to do before. Organisms got larger. That was the first visible change, and the most significant one in the long run. For most of the history of life on Earth, the largest creatures had been microbial mats, colonies of single cells bound together by chemistry rather than biology. Individual organisms had stayed microscopic. Multicellularity had evolved many times independently, in algae and in certain fungi and in a handful of other lineages, but it had stayed simple. Blobs of cells, filaments, nothing that looked from the outside like a body. The reason size had been constrained was oxygen. A large organism, especially a motile one, needs to move a lot of oxygen through its tissues to fuel the metabolism that keeps it alive. The surface-to-volume ratio drops as bodies get bigger, so diffusion alone cannot deliver enough oxygen past a certain size. Circulation systems help, but they also cost energy and require more oxygen themselves. The upper limit on body size in a low oxygen world is severe. Raise the oxygen level, even modestly, and that limit moves upward. In the sediments laid down in the 100 million years after the Marinoan, you can watch the limit moving. The fossils get bigger, they get stranger. They develop features that look like bodies in a way nothing in the earlier record does. By 630 million years ago, roughly 5 million years after the last cap carbonates precipitated, something in the oceans had started building itself into shapes that had never existed on this planet before. The first thing you need to understand about the creatures that appeared in the oceans after the Marinoan is that they looked almost nothing like anything alive today. Not like modern animals, not like earlier animals, because there were no earlier animals, not like the algae or microbial mats that had dominated every ocean before them. These things had bodies, but the bodies did not follow any of the rules that would later define animal life. No mouths, no guts, no heads, no legs, no eyes. Most of them were soft, quilted, leaf-shaped or disc-shaped or frond-shaped, lying flat on the seafloor or anchored to it by slender stalks. They ranged from a few centimeters to more than a meter across. And for something like 80 million years, they were the largest and most complex visible organisms on Earth. Geologists call them the Ediacaran biota, after the Ediacara Hills in South Australia, where they were first described in detail in the 1940s. Reginald Sprigg, a young Australian mining geologist, found the first specimens in 1946, fossils of soft-bodied organisms preserved as impressions in sandstone. He thought at first they were jellyfish. The scientific community was skeptical for years that soft tissue could have fossilized at all in rocks that old, and it took until the 1960s for the Ediacaran fossils to be accepted as genuine. Since then, they have been found on nearly every continent. In Newfoundland, in Russia's White Sea, in Namibia, in southern China, in the Urals, in northwestern Canada. Everywhere the right kind of rock from the right period has been preserved, the strange impressions turn up. The individual organisms have names that sound like they came from a field guide written for a different planet. Dickinsonia, the flat oval with segments running across its body like a quilted pillow. Charnia, the frond-like creature that looked almost exactly like a modern sea pen but had no relationship to one. Kimberella, a slug-shaped thing with what might have been a muscular foot. Sprigina, named after Reginald Sprigg, a small segmented creature that some researchers have tried to link to arthropods and others have argued is something else entirely. Tribrachidium, a disc with 3 arms radiating from its center, a body plan unlike any that survived into later animal phyla. Pteridinium, Rangea, Swartpuntia. Most of them are not closely related to anything alive now. Many of them are not closely related to each other. For a long time, the debate in paleontology was whether these things were animals at all. The Ediacaran biota shows up about 635 million years ago, shortly after the Marinoan cap carbonates, and flourishes until about 540 million years ago, when almost all of them vanish from the rock record just before the Cambrian explosion. That is an 80 million year reign of soft-bodied, sessile, mostly stationary organisms that look like nothing else in the history of life. Some researchers argued they were a failed experiment, an independent branch of multicellular life that evolved after the snowball, hit a dead end, and died out completely. Others argued they were early animals in a broad sense, relatives of the lineages that gave rise to the Cambrian fauna. The question has not been fully resolved even now, because the fossils preserve so little of the internal anatomy. What remains is mostly the outline, the surface texture, the vague shape. Enough to know the organisms existed, not always enough to know exactly what they were. What is clearer is what they were doing. Most of the Ediacaran creatures lived on or near the seafloor, resting against microbial mats that carpeted the shallow tropical oceans. Some of them appear to have absorbed nutrients directly through their body surfaces, like modern sponges do, without any kind of digestive system. Others, like Dickinsonia, may have fed by resting on microbial mats and digesting the mat beneath them from the outside, leaving behind oval depressions where they had grazed. There is evidence of movement, though slow. Trails in the sediment, patches of disturbed mat. The first trace fossils in the history of life that show any creature moving from one place to another under its own power. It is worth pausing on how strange this is, because the familiarity of modern biology can make it hard to feel the novelty of what was happening. For more than 3 billion years, life on Earth had been microscopic. If you could have gone diving in a pre-Cryogenian ocean, you would have seen mostly clear blue water with the occasional algal mat or microbial biofilm on a rock. Nothing moving. Nothing with a shape big enough to notice without a microscope. The Ediacaran oceans were different. They had things you could see from a distance, things you could point at, things that had individual outlines against the sediment, bodies that took up space, creatures in a sense that nothing on Earth had ever been a creature before. If you had swum through those seas, you would have seen gardens of strange flat quilts and branching fronds and sluggish movers spread across every continental shelf where the light reached, patches of them the size of meadows, fields of them stretching for kilometers. The most important Ediacaran site in the world, by the accident of preservation, is in a place we have already been. Namibia. The same outcrops where Hoffman mapped the cap carbonates turn out when you walk a little further up the stratigraphic column to hold some of the best preserved Ediacaran fossils on Earth. Pteridinium, Swartpuntia, Rangea, and a creature called Namacalathus, which built small goblet-shaped structures out of calcium carbonate. The preservation is extraordinary because the sediments at the time were draped over microbial mats that, when they decomposed, formed a kind of death mask around the bodies pressed into them. What you find when you split open one of those slabs of Namibian shale is the outline of a creature that died 600 million years ago, preserved in the cast of a microbial skin that settled over it. Those same Namibian rocks have produced another kind of fossil, smaller but in some ways more important, because it pushes the origin of animal life back earlier than the Ediacaran biota itself. The name of the organism is Otavia antiqua, and it is, or appears to be, an early sponge. Sponges are the most primitive animals alive today, filter feeders that pump water through their bodies to extract food particles, lacking true tissues, but clearly meeting any biological definition of an animal. Otavia was discovered in 2012 by a team led by Anthony Prave at the University of St Andrews, working with colleagues from Namibia and South Africa. What they found were microscopic fossils, fractions of a millimeter across, with the internal structure of a sponge, pores for water intake, chambers, an excurrent opening, the characteristic calcium phosphate skeleton. The fossils appear in rocks that predate the Sturtian glaciation. They continue through the interglacial, through the Marinoan, through the deglaciation, into the full Ediacaran. Otavia, or something very much like it, survived both snowball events. If the identification is correct, and the debate about this is ongoing, then animals were already present on the planet before the first freeze. Sponges were waiting out the ice in whatever refuges they could find, and came through the other side ready to diversify when conditions allowed. This reframes the Snowball Earth story in an important way. The ice did not create animal life. The ice filtered it. Whatever lineages made it through had to be able to survive tens of millions of years of extreme cold, low food, limited oxygen, and minimal open water. What emerged on the other side was not a new creation, but a selected remnant of what had already existed, now faced with an ocean full of phosphorus and oxygen, and a relaxed metabolic ceiling. Those conditions let the survivors radiate into forms they could never have taken before. The body plans exploded because the constraints had loosened, not because the organisms had appeared from nowhere. There is a pattern here that shows up again and again in the history of life. A mass extinction or a long environmental bottleneck removes most of what exists. The survivors, operating in a suddenly emptier world with new resources available, radiate rapidly. New forms appear. Some of them persist, some of them fail. The biosphere reorganizes itself around the new conditions. What happened after the Marinoan was not a mass extinction in the ordinary sense, but it functioned like one because the ice had killed almost everything that could not tolerate it. The survivors inherited a world that had been cleared of competition and flooded with nutrients, and they built the first visible ecosystems on that foundation. For 80 million years, those ecosystems belonged to the Ediacaran creatures. Then, around 540 million years ago, something changed again. The soft-bodied organisms began to disappear from the fossil record. New fossils appeared in their place, creatures with hard shells, with mouths that could bite, with eyes that could see, with limbs that could swim or burrow. The Cambrian, the event that gave rise to essentially every major branch of animal life that exists today, including the ones that led, through 500 million years of continued evolution, to the creature listening to this. The Cambrian is a story for another night, but it could not have happened without what came before it. Without the 60 million combined years of ice that killed off most of the competition. Without the phosphorus flood that raised the oxygen ceiling. Without the 80 million years of Ediacaran experimentation, the body plans tried and abandoned, the slow accumulation of biological complexity in warm post-snowball seas. The frozen Earth did not give birth to animal life. What it did was arrange the conditions under which animal life could finally become visible, could finally move, could finally, after 3 billion years of microbial quiet, take shape. Which leaves one question still hanging over this whole story, the question that keeps coming back whenever anyone thinks seriously about what the snowball did to the planet's thermostat. If the Earth could freeze that completely, twice in quick succession, in an interval of less than 100 million years, then why has it not happened since? 635 million years have passed since the last snowball ended. The thermostat has held. No tropical glaciers, no total freezes, not one across every climate fluctuation the planet has experienced, through every ice age and greenhouse and extinction event. Something changed after the Cryogenian, something deep in the way the Earth handles its carbon budget, and understanding that change is the last piece of the puzzle. The question of why the Earth has not frozen again in 635 million years sounds, at first, like it should have a simple answer. Something changed. The conditions that allowed a runaway freeze in the Cryogenian no longer apply. The continents drifted, the sun got brighter, the biosphere evolved. Any of these could be the reason, and for a long time, any of them might have been offered as a partial explanation. But over the last decade, and especially in a paper published in 2024 by Adriana Dutkiewicz and a team at the University of Sydney, the picture has sharpened considerably. What they showed is that the Cryogenian was not a close call that the Earth narrowly escaped. It was a unique window, a configuration of the planet's interior that produced conditions for global freezing and that once closed has never reopened. The key, it turns out, is volcanoes. Not the ones you see on the surface, though those matter too. The ones that run silently along the mid-ocean ridges, where new ocean crust is being born every day at rates measured in centimeters per year. Every kilometre of new seafloor that forms at a mid-ocean ridge releases carbon dioxide from the mantle. Every zone where old crust is pushed back down into the mantle at a subduction zone eventually cooks that crust and releases more carbon dioxide through volcanic arcs. The total amount of carbon dioxide that enters the atmosphere from these tectonic processes is the global outgassing rate, and over the course of Earth's history, it has varied considerably. During the late Neoproterozoic, in the stretch of time that included the Cryogenian, the global outgassing rate was anomalously low. Dutkiewicz and her colleagues calculated this by reconstructing the length of mid-ocean ridges and the rate of seafloor spreading throughout Earth's history, using plate tectonic models constrained by paleomagnetic data and the global record of ocean floor age. Their result was striking. Across the late Neoproterozoic, the total length of active mid-ocean ridges was shorter than at almost any other time in the past billion years. Fewer ridges meant less new crust, which meant less carbon dioxide entering the atmosphere from the mantle. The baseline supply of greenhouse gas was running at perhaps half its modern value, possibly less. This is the condition that made the Cryogenian possible. A low outgassing Earth is a cold-leaning Earth, all other factors being equal. When the Franklin erupted and began pulling additional carbon dioxide out of the atmosphere through basalt weathering, the world could not compensate fast enough because the volcanic supply was already weak. The thermostat had less fuel than usual, a perturbation that might, under normal conditions, have produced a moderate cooling, instead produced a runaway. The planet slipped past the albedo threshold. The ice took over. What happened after the Cryogenian was that this tectonic configuration changed, and changed permanently. The supercontinent Rodinia, which had been quietly holding itself together even as the Snowball Earths came and went, finally finished breaking apart during and after the Marinoan. The fragments drifted, colliding with each other, building new ocean basins between them. Those new ocean basins required new mid-ocean ridges, and every new ridge meant new carbon dioxide flowing into the atmosphere. The global outgassing rate rose. Dudkiewicz's reconstruction shows the rate climbing through the Ediacaran, doubling by the early Cambrian and remaining elevated throughout the subsequent 500 million years of Phanerozoic time. The Earth became a warmer-leaning planet, not because the climate itself changed, but because the deep Earth was producing more greenhouse gas in a sustained way than it had during the Cryogenian. At the same time, something else changed. The breakup of Rodinia opened new coastlines, new shallow seas, new places where biology could take hold. Life had been marginal on the continents throughout the Precambrian, confined to microbial films and the occasional algal crust. With the radiation of the Ediacaran biota and the Cambrian fauna that followed, the biosphere began to have a measurable effect on chemistry at planetary scales. More organisms meant more organic carbon buried in sediments, which meant more carbon removed from the atmosphere-ocean system on long timescales. But the larger effect, the one that mattered for climate stability, was that the post-cryogenian biosphere had much more oxygen to work with. The oceans stopped being chronically anoxic at depth. The chemistry of the seafloor changed. Seafloor weathering, which had been so efficient at drawing down carbon dioxide during the Sturtian, lost some of its grip on the carbon cycle because the deep oceans were no longer as acidic or as reactive. Even later, something more significant arrived. Plants. Actual plants with roots and vascular tissue colonizing the continents for the first time during the Ordovician and Silurian periods, 400 to 500 million years ago. Plants transformed continental weathering because they dramatically accelerated the chemical breakdown of rocks. Roots pumped carbon dioxide into the soil. Mycorrhizal fungi partnered with the roots, pulled minerals out of stone at rates no abiotic process could match. The weathering feedback became stronger, more responsive. When carbon dioxide rose, plants weathered more rock and pulled it back down faster. When carbon dioxide fell, weathering slowed. The thermostat became both more reliable and more tightly tuned. The combined effect of higher outgassing and a biologically regulated weathering response is a climate system that simply cannot produce a snowball Earth under normal conditions. The feedback loops are too strong in the stabilizing direction. You can push the planet into an ice age, as the Pleistocene has demonstrated repeatedly over the last 2.5 million years. You can drive it into a greenhouse, as the Paleocene-Eocene thermal maximum showed 56 million years ago when a burst of carbon released from the deep ocean raised global temperatures by 5 to 8 degrees. What you cannot do with the current tectonic and biological configuration of the planet is freeze it all the way to the equator. The thermostat catches the swing long before it reaches that extreme. This is not a minor finding. It matters for our understanding of planetary habitability in general, not just for Earth. When astronomers look at rocky exoplanets in the habitable zones of other stars, they assume those worlds can sustain liquid water somewhere on their surfaces. But the habitable zone is a rough guide, and planets within it can still, in principle, slip into frozen states if their tectonic or atmospheric conditions permit. Earth came through that test twice, and both times it required 56 million years the first time, or 4 million the second, for the volcanoes to provide enough carbon dioxide to break the freeze. Other worlds, with different volcanic rates, different continental configurations, different atmospheric compositions, might get stuck. A snowball that starts on an exoplanet with too little volcanic outgassing might not have an exit. There is an uncomfortable implication in this, which is that the long-term habitability of a rocky planet depends critically on processes that have nothing to do with the presence or absence of liquid water. It depends on the deep interior, on how fast heat is flowing out of the mantle, on whether plate tectonics is active, on the balance between carbon entering the atmosphere from below and carbon leaving it through weathering and burial. These are slow processes, mostly invisible from space, and they determine whether a planet stays habitable across billions of years or whether it drifts into one of the stable attractor states from which there is no easy return. A frozen Earth is one such state. A runaway greenhouse, like Venus's, is another. The narrow band of conditions that keeps a planet oscillating gently between warm and cool extremes without ever falling off one of those cliffs is narrower than it looks. The Earth has been in that narrow band for the entire Phanerozoic. Every ice age it has experienced, from the Ordovician glaciations 440 million years ago to the Permo-Carboniferous ice sheets 300 million years ago to the Pleistocene glacials of the last 2.5 million years, has been a partial event. The tropics remained ice-free. The oceans remained oxygenated at depth. The carbon budget remained manageable. At no point in the last 635 million years has the planet come close to a total freeze. But this does not mean the climate system has been passive. It has been working all along against the same feedback loops that drove the Cryogenian, but with a thermostat that has more tools at its disposal. Plants accelerating weathering, animals burying organic carbon, continental positions that keep the tropics open, an outgassing rate high enough to prevent carbon starvation in the atmosphere. These are the reasons Earth has stayed habitable for complex life across 500 million years. They are also the reasons the planet will, almost certainly, continue to stay habitable for a long time on its own. The problem is that the thermostat, for the first time in 635 million years, is being pushed by something that operates faster than any of its natural feedbacks can respond to. The comparison is not an easy one to make without sounding alarmist, and the relevant timescales are all different from the ones the Earth has evolved to handle. But it needs to be made because the story of Snowball Earth is not just about a frozen planet in the deep past. It is about how climate systems behave when they are pushed hard enough by forces that overwhelm the usual balancing mechanisms, and what happens when those pushes come from outside the slow machinery of the deep Earth. The Cryogenian was pushed by a volcanic province and a set of tectonic conditions that lasted millions of years. What is happening now is faster and smaller and in some ways more alarming because the scale of the forcing is comparable to what those ancient events produced, but the timescale is compressed into something the planet has never had to handle before. There is a version of the ice-albedo feedback that is running on the Earth right now. It is not producing a snowball, it is producing the opposite. But the physics is the same physics, operating by the same rules that Kirschvink and Boudico and Sellers laid out decades ago, and if you understand what happened during the Cryogenian, you already understand what is happening at the poles today. The direction has flipped, the time scale has compressed, the underlying mechanism is identical. In the Arctic Ocean, sea ice has been shrinking for 4 decades, measured by satellites that track the extent of the ice through every summer and every winter. The rate of loss has not been uniform. Some years the ice recovers partially, other years it collapses. But the long-term trend is unmistakable. Summer sea ice covered an average of about 7 million square kilometers in the early 1980s. By the early 2020s, it had dropped to about 4.5. By 2025, the figure was still dropping, with some models suggesting ice-free Arctic summers sometime in the 2030s or 2040s. What is happening there is the same feedback loop that trapped the Cryogenian, playing out in reverse. When sea ice melts, it exposes dark ocean water beneath. The ocean absorbs roughly 94% of the sunlight that falls on it, the near mirror image of the 92% that fresh ice reflects. A patch of open water where ice used to sit is suddenly absorbing an enormous amount of additional solar energy. That energy warms the water. The warmer water resists refreezing the following winter. less ice forms. More ocean stays exposed. The feedback compounds. The Arctic has been warming at roughly 4 times the global average rate for exactly this reason. Climatologists sometimes call it Arctic amplification, but the underlying mechanism is the ice-albedo feedback, the same one Kirschvink invoked in 1992 to explain how the Cryogenian ever ended. The difference between then and now is a matter of speed, and the speed is the thing that matters most. During the Cryogenian, carbon dioxide entered the atmosphere at a rate set by plate tectonics and volcanic outgassing. That rate was low. Across the 56 million years of the Sturtian, atmospheric carbon dioxide might have risen from a few hundred parts per million to something like 10% of the atmosphere, a factor of roughly 250. The rate of rise, averaged across those millions of years, was a tiny fraction of a part per million per year. The Earth's carbon cycle has evolved to handle changes on that kind of timescale. Weathering adjusts, ocean chemistry equilibrates, biological feedbacks compensate. The thermostat has enormous power, but it works slowly across geological time. Human beings have been adding carbon dioxide to the atmosphere through the burning of fossil fuels and changes in land use at a rate that is completely outside the range the thermostat was calibrated for. In 1850, atmospheric carbon dioxide was around 280 parts per million. In 2025, it was around 425. That is a rise of about 145 parts per million in 175 years. Averaged out, that is a little under 1 part per million per year, but the rate has accelerated. Recent years have seen rises of 2 to 3 parts per million annually. The current rate of atmospheric carbon dioxide increase is, by the best reconstructions geochemists have been able to assemble from ice cores and deep-sea sediments, somewhere between 10 and 100 times faster than any sustained natural increase in the past 66 million years, possibly faster than anything in the last 500 million. The comparison that matters most here is to the Paleocene-Eocene thermal maximum, the carbon release event I mentioned earlier. 56 million years ago, something released an enormous quantity of carbon to the atmosphere over a span that used to be estimated at 10,000 years and is now, with better dating, thought to be closer to 3 to 5,000. Global temperatures rose by 5 to 8 degrees, the oceans warmed, deep-sea ecosystems suffered a mass extinction. It is the closest analogue in the recent geological record to what modern carbon emissions are doing. But when geologists and climatologists have compared the rates carefully in studies like the one by Philip Gingerich in 2019, the finding is that modern carbon emissions are running about 9 to 10 times faster than the PETM on the relevant timescales. We are compressing into centuries what the PETM took millennia to accomplish. For the ice-albedo feedback, this speed is everything. A slow forcing over millions of years gives the climate system time to respond through all its available feedbacks. Rock weathering speeds up, biological uptake adjusts, ocean chemistry buffers, temperature changes spread through the system gradually and equilibrate. A fast forcing does none of that. The feedback loops that depend on long timescales simply do not have time to act. What you get instead is the short timescale feedbacks operating on their own, including the ice-albedo feedback, which runs on the decadal to centennial scale rather than the million-year scale. This is why the Arctic is warming so fast. It is not that the ice-albedo feedback is stronger than it was in the Cryogenian. It is that there is nothing slow enough to oppose it on the timescale it is operating. The weathering thermostat is still working somewhere in the background, grinding through its millennium-scale adjustments, but it cannot respond to a century-scale forcing. The climate system is, in effect, being pushed by a mechanism faster than most of its own stabilizers. There is a kind of dark symmetry to what is happening. During the Cryogenian, the planet was pushed into a frozen state through a slow drawdown of atmospheric carbon dioxide, driven by basalt weathering on a tropical supercontinent. The runaway ice-albedo feedback took the rest. It took 56 million years for the volcanoes to restore enough carbon dioxide to break the freeze. Today, we are running the same feedback in the opposite direction, through a rapid injection of carbon dioxide back into the atmosphere at a rate that no slow natural feedback can match. The ice is retreating instead of advancing. The ocean is absorbing more solar energy instead of less. And there is no obvious equivalent of the weathering thermostat to pull things back. Not in the timescales that matter to us anyway. The thermostat will eventually catch up. It always does. Over the next several 100,000 years, the excess carbon dioxide will be slowly pulled out of the atmosphere by enhanced weathering and ocean chemistry, and the climate will drift back towards something closer to the pre-industrial baseline. But the planet will not be in a hurry, and the ecosystems that matter to us, the ones we have built our civilization around, operate on much shorter timescales than that. Imagine for a moment a geologist working 100 million years from now. She is not human. Her species, whatever it is, has evolved on whatever version of the Earth has come into being by then. She is looking at a thin, dark band in a cliff face, a layer of sediment just a few centimeters thick. In it, she finds the carbon isotope signature of an enormous sudden perturbation to the global carbon cycle. The values are disturbed in a way that does not look like any of the ordinary patterns. Not volcanic, not an asteroid. Something else, compressed into a vanishingly thin slice of the rock record. She traces the signature across continents. Everywhere it appears, it is brief. Everywhere it appears, it is unusual. And the rocks immediately above it show signs of a mass extinction that fell most heavily on certain groups, while others survived and eventually recovered. She will have a name for what she is looking at. We do not know what she will call it, but she will know that something happened, something short and intense and chemically strange in the deep past of her planet. If she is skilled, she might trace the signal back to the specific years in which most of the carbon was released. She might even work out from the isotopic composition that the carbon was enriched in the lighter isotope characteristic of biological material, of long-buried organic matter, of the kind of carbon that comes from burning coal and oil and gas. She might notice that the event coincides with the disappearance of many species and the sudden shift of others toward colder latitudes and higher altitudes. What she will not find is the explanation. The rocks do not record intentions, and they do not record actors. They record effects. 10 million years from now, the species responsible for this disturbance will be as invisible to her as the Cryogenian volcanoes are to us. All she will see is the signal, a spike in carbon, a collapse of certain ecosystems, a long recovery. Something that happened, and something that the planet dealt with eventually. In the slow way the planet deals with everything. The Earth will be fine. This is the hardest and most important thing to say clearly, because it is easy to confuse with indifference. The planet will outlast us by billions of years. It will handle whatever carbon we release, eventually, through mechanisms that have handled larger perturbations in the past. 56 million years of global ice. Asteroid impacts that restructured the entire biosphere, volcanic events that sterilized whole ocean basins. The Earth absorbs these events and continues. It will absorb ours. What will not continue, necessarily, is us, or the particular configuration of ecosystems, climates, coastlines, and ranges that we have spent 10,000 years building our civilization around. The thermostat is not malfunctioning. It is just operating on a time scale that is not useful to us. And the question, when you step back and look at the whole arc of Snowball Earth, is not whether the planet will recover. the planet always recovers. The question is whether the recovery will include anyone who remembers what happened, which brings the story back at the end to where it began, to a world that froze solid twice and came back both times, to the lineages that made it through, to the long, patient process by which ice and carbon and time sorted the living world into something complex enough to sit somewhere tonight, warm and breathing, and hear itself wondering about the planet that produced it. Somewhere in the Namibian desert, in a canyon Paul Hoffman has walked 100 times, there is a single flat bedding plane where you can put your hand across a transition that shaped everything. On one side of the line, the rock is chaotic, full of drop stones and pebbles and the jumbled debris of an ice sheet that had been grinding across the seafloor for 4 million years. On the other side, it is smooth, fine-grained, pale dolostone, the kind that forms in warm, shallow, tropical water. You can run a finger from one to the other. You can cross, in the space of about a centimetre of rock, from a world buried in ice to a world that had, by every available measurement, returned to something almost like the present. The width of that contact, in geological terms, is zero. There is no gradient, no slow thaw preserved in the sediments, no interval where the climate was intermediate, hesitating between one state and the other. Just the ice, and then the warm sea, with nothing in between. It is the clearest signature Earth has ever recorded of how quickly a planet can move between its stable configurations once the feedback that holds it in place gives way. And it is the physical reminder that all the things we have been talking about tonight across the full length of this story actually happened, not as theory, not as model, as stratigraphy. The hand you would use to touch that bedding plane, the hand attached to whoever is listening to this right now, descends in a very long chain from organisms that were alive during that transition, not the visible, complicated ones. The Ediacara and Biota, for all their strangeness, are not your direct ancestors. The fronds and quilts and disc-shaped creatures of the post-Marinoan seafloor are mostly sidelines, evolutionary experiments that flourished for 80 million years and then disappeared when the Cambrian fauna arrived. What passed through that canyon in its earliest, smallest form was something less impressive. Single cells, microbial mats, a few lineages of early sponges, not much larger than the grains of sand preserved around them, making a living on whatever food the post-Snowball Sea could offer. Otavia, or something like Otavia. Creatures no one would have looked at twice, and yet those were the links. The organisms that survived both snowball events in whatever refuges were available, carrying forward the biochemical apparatus that every living thing on Earth still uses. The DNA replication machinery, the ribosomes, the metabolic pathways for building proteins and burning sugars and pumping ions across membranes. All of that already existed before the Cryogenian started. All of it passed through 60 million cumulative years of ice and came out the other side, still working, still capable of building something bigger when the conditions allowed. What happened in the post-Marinoan oceans was not the invention of complex life. It was the release of complex life into a space where it was finally allowed to grow. It is worth holding that thought for a moment, because the version of the Snowball Earth story you sometimes hear, the simple version, says that the ice killed off the old biosphere and the thaw created the new one. That is not quite right. The ice filtered, the thaw amplified. What came through the filter had been there all along, hidden in microbial mats and cryoconite holes and subglacial meltwater, quietly encoding the potential that would eventually produce every plant and fish and bird and mammal that has ever lived, including the one breathing now on whatever side of whatever planet, with the voice of a recording speaking quietly in the background as sleep approaches. There is something about the timescales that I want to come back to one more time before we are finished, because they are, in the end, the hardest part of the story to hold. The Sturtian lasted 56 million years. The Marinoan lasted 4. The Ediacaran reign that followed stretched for another 80. The Cambrian opened 540 million years ago. The dinosaurs arose and fell entirely within the most recent third of the time since the last cap carbonate was laid down. The whole history of mammals, from the first furry creatures scurrying around at the dinosaurs' feet to the human beings now putting podcasts on the internet, is about 200 million years, less than a third of the interval between Otavia's earliest fossils and tonight. These numbers are impossible to visualize. No one, not even the geologists who spend their lives working with them, truly feels the weight of 56 million years. The best you can do is to lay one interval against another and watch the proportions shift. The entire existence of your species, from the first Homo sapiens in East Africa to the last human breath, whenever that comes, is probably going to occupy somewhere between a few 100,000 and a million years. A good run by the standards of most mammalian species. A tiny slice of Cryogenian time. If you could fit the entire history of anatomically modern humans into a single year, the Sturtian glaciation would last more than 50 such years, and the period of relatively warm climate in which your civilization was built, the last 10,000 years since the end of the Pleistocene, would last 2 hours. That is the kind of story the rocks are telling. A planet that has been running much longer than any observer it has ever produced, along rhythms that are not tuned to anyone in particular, through configurations that are sometimes comfortable and sometimes not. The Cryogenian was not comfortable. The super greenhouse that followed it was not comfortable. The many ice ages and hothouses since have not been uniformly comfortable. The planet does not grade its own performance. It simply passes through its states, one after another, in the order the physics and the chemistry and the biology dictate. And yet something keeps coming through. That is the part I want to leave you with as the audio slows toward the end. Not a lesson, not a warning, just the fact that in every one of those transitions, something on this planet held on. Through the first snowball, something held on. Through the second, something held on. Through the Permian extinction 252 million years ago, when 96% of marine species died, something held on. Through the Cretaceous extinction 66 million years ago, when the asteroid arrived and the dinosaurs fell, something held on. Every single time, against every set of odds the planet has offered, some lineage of the living has been stubborn enough, or small enough, or lucky enough to come through. The line you are on, the genetic line that produced the ears hearing this and the brain making sense of it, has not broken once in 3.5 billion years. Not during any of the snowballs, not during any of the mass extinctions, not during any of the ordinary daily catastrophes of predation and disease and bad luck that have killed most individuals of most species across most of the history of life. Every ancestor you have, going back to the first self-replicating molecules, survived long enough to produce the next ancestor. Every one of them. Not one break, not one failure. An unbroken chain, microbial on one end and human on the other, held together by nothing more dramatic than the fact that in every generation, against every pressure, enough of your ancestors kept going. That is the snowball's real gift, if you want to frame it that way. Not the oxygen, not the phosphorus, not the body plans, just the proof, written in rock on every continent, that a planet can freeze over twice, and life can come through both freezes and eventually become something capable of finding out what happened. The Cryogenian was a test. The test was extreme, and on the other side of the test, there was, eventually, you. That is worth sleeping on. The planet does not need you to worry about it. The planet has done this before. We'll do it again. We'll continue across timescales that dwarf every ambition anyone has ever had, through the slow work of plate tectonics and volcanic outgassing and the patient accumulation of new conditions. The oceans will warm and cool, the ice caps will grow and shrink, the continents will keep drifting toward whatever next supercontinent is slowly assembling itself out of the fragments of the current arrangement. None of this is anxious, none of it is hurried. The Earth is in no rush. What you are, lying there now, is the current expression of an experiment that began 3.5 billion years ago and has continued, without interruption, through every bad chapter the planet has offered. You are a kind of archive, in a way that has nothing to do with memory. You are what came through, the ice in the tropics, the oxygen in the seas, the sponges in the shallows, the strange gardens of the Ediacaran, the first animals that could move, the fish, the tetrapods, the mammals, the primates, the ancestors. All of them passed the thing they were carrying along, generation after generation, through worse conditions than tonight will ever offer, until at last it arrived with you, here, under whatever roof is over your head, with the heating on or off, with the window cracked or closed, with sleep coming on slowly or quickly, depending on the kind of night it is. You do not have to think about any of it anymore. You have already done the hardest part, which was simply existing long enough to be the one listening. The next thing on the list, if there is a list, is rest. The ancestors are not going anywhere. Neither is the planet. Neither is the story. All of it will still be here in the morning, arranged exactly as it has always been arranged, waiting for whenever you are ready to pick it back up. Until then, somewhere in the dark, an ice sheet is retreating. Somewhere else, a new one is beginning to form. Cyanobacteria are blooming in a tropical sea, doing the same work they have done for 3 billion years. An Ediacaran fossil is sitting in a Namibian cliff, preserved exactly as it was when the mud settled over it. Paul Hoffman is probably asleep at whatever hour it is where he lives now. The Garvalach rocks are sitting under a cold Scottish sky. The planet is doing what the planet has always done, which is keeping on, without fuss, without drama, one day at a time, for as long as anyone can reasonably ask it to. That is enough for tonight. Rest. The planet is still here. The chain is still unbroken. And whatever you were carrying when this started, whatever worry or question or small trouble brought you to a story about ice that fell 600 million years ago, you can set it down now. It will still be there when you wake. So will the ice, so will the sea, so will you. Good night.